We might be live. Let's see. Hello everyone. Can somebody write in the chat to confirm that we are actually live and that most importantly that the audio is working? I haven't streamed in a while, and every time you start from a new hardware, or it's new hardware, it's new software, I don't know, I had to change my monitor resolution because OBS wasn't in the fractional scaling and stuff, so hopefully things work. The YouTube thing seems to say it does. It's a little wonky. So the audio works, right? All right, so let's assume it is working. There is no real agenda for today, or I might talk a little bit about some stuff I've been working on. We'll see. So the last time I've streamed this in this format, I think was maybe a year ago. I used to do this more often. Oh, hey Aras, hey Pavel. The point is just to talk about stuff. Maybe people have questions about general programming things. Maybe people have questions about what I have been doing, what I'm planning to do, etc. But yeah, the idea is to just spend a couple hours on the stream. I have a whiteboard thing in case we need it. Let me double check that works. Oh. All right, it sort of works. I have to recenter it, of course. All right, so if people have things that they want me to talk about, please just say so in chat. I'm happy to cover all topics. Maybe let me just start a little bit. I haven't really announced this as such or whatever, but if people have seen me posting content about machine learning related concepts that I haven't really posted about before, let me talk a little bit about this and then we'll see where we're going. So obviously ML is all the rage right now, and for good reasons and bad reasons. There's things I like about this whole world and there is a lot of things that I don't like. I can talk more about this maybe, but generally I think early this year I kind of realized there is this big tool that's missing from my toolbox, which a lot of people seem to be excited about. And earlier this year I spent a bunch of time sort of going through a few courses, training networks, learning, reading papers, writing code, stuff like that. So that is all fun and good. As usual, I am 10 years late to the party because when I was doing this early this year, the world was already moving in the direction of less specialized machine learning models and more general language is all you need. Let's just train an artificial sentient being that will solve all the problems for us. But I spent time learning about the actually older things, things like computer vision as it applies to machine learning, CNNs, LSTMs, reinforcement learning, all of that stuff. So that was all fun. There's things I liked about this, there's things I didn't like about this. What I've been doing for the last few weeks is something kind of different, but kind of similar, and it's been a lot of fun. So I have this project. Hello people. A lot of people I know, which is good. Because all familiar faces. So there's this project that I started a few weeks ago where here's the general if you look at what people are doing right now around like machine learning and language models and stuff like this, there's a lot of different directions. One kind of one thing I don't like about the ML field in general is how deep the stacks tend to go and how kind of flaky everything seems. What I mean by this, so if you look at what I've been doing earlier this year, for example, is I've been training a bunch of networks and I've been using PyTorch for this. So PyTorch is like a Python-based neural network library, uh, which has GPU acceleration as one does these days and all of that stuff. So it's like reasonably fast. But what you're fundamentally dealing with is this complex layer cake where there is PyTorch at the top. Maybe there's not even PyTorch at the top. There's like stuff above PyTorch. But let's just say there's PyTorch at the top. And then PyTorch, of course, is implemented in, or large parts of PyTorch are implemented in C++. A lot of this is like custom code that maybe uses SIMD intrinsics or OpenMP or whatever to accelerate things on CPU. So then there's also CUDA, of course, which is the NVIDIA sort of set of libraries. Specifically, PyTorch doesn't just use raw CUDA, it uses, I think, other libraries as well, like cuBLAS or whatever, to accelerate individual operations. So then, of course, the code that CUDA produces runs on your actual GPU, right? And then there's other things. So there's sort of this set of layers that you have to navigate through, and maybe there's a feature that's supported on the CUDA layer, but it is not supported at the PyTorch layer, and to make it work, you have to like change the layers in the middle. There's also other libraries, so PyTorch doesn't support a lot of the things that you actually really need for sort of efficiency reasons. They're getting better and better at this quickly, but the state early this year was, oh hey, you want to do something custom and like neat, you have to have some extra module. And so, for example, people have extra modules that are integrated with PyTorch that they have written, so you install like a separate library. I don't know, there's like this thing called bits and bytes, which is also this hybrid Python C++ CUDA thing, which integrates with PyTorch, also goes to C++, also goes to CUDA. And there's a lot more to this stack. Like I could keep drawing letters and drawing errors, but the whole thing is kind of complicated to get going. And then one other thing that's kind of annoying about all of this is a lot of this stuff is JIT compiled. And if you don't JIT compile a lot of these things, then you're leaving a lot of performance on the table. There's this problem that is really critical for you to be able to run any of this code efficiently, which is the way you are implementing things in PyTorch. You are working on these giant arrays of numbers on giant matrices, and you are using primitive operations. So you have, let's say, A times B times C, where times is here just a component-wise multiplication. And A, B, and C are like insanely large matrices, like a gigabyte of numbers or something. So let's say you're doing 2-point-wise multiplications. By default, what happens is PyTorch takes this thing and says, oh, cool, I'm going to create a new tensor or like a matrix that's the result of this operation. Do this operation, save the results to memory. All of this might be stored on your GPU, but the bulk of the cost is actually kind of loading numbers from memory, from video memory, and storing them back to video memory. And then, the times C will be like one more thing. So A times B gives you T. So then you do T times C. This produces the result. All of this stuff is slow. So then PyTorch has, and this is slow because instead of running one CUDA kernel that loads everything from memory, does the operations optimally, and then saves the results back, you run multiple kernels step by step, and then all of the operations are routed through video memory. So to solve this problem, PyTorch has a set of like extra things on top of PyTorch or embedded into PyTorch, depending on how you look at this, which do this graph compile thing where they say, oh, look at your function, it does a times b times c. I know how to take this and compile this into a CUDA, like single CUDA kernel that does all of this efficiently. But all of this stuff, so it works. There is like a lot of problems. I won't go deep into this, but generally, essentially, I look at this and I am simultaneously fascinated and horrified by all of this, because everything is like, to actually understand what your system is doing, you have to like look through 15 layers and then like debug them and then optimize them and figure things out. So what instead I started is just to play around with things, is I started a project where we bypass all of this. There is just CUDA and GPU. There's not even C++, there is just C, because C++ is for, I don't know, for real production, and C is for enthusiasts or whatever. So there is a reason why I'm using C, but it's also to like force this minimal complexity regime. And then if you just had CUDA and just had the GPU, could you write some code that optimally, that takes a language model, like an open source language model, as in the weights are available, and then runs it on your GPU and then produces results and produces them quickly. Anyway, so that's what I've been doing for the last couple weeks, 3 weeks. It's been a lot of fun. It's a lot of like learning new things, rediscovering things I used to know way back when, but forgot. And just in general, it's like an interesting space to be in. Let me run. I guess I have like a demo. Well, this is a bad demo. Let's hope this stream survives. Oh, I had some fun with hardware setup. I'm gonna talk a little bit about this, but yeah. So the way this is set up right now, not sure if you can see this. Hopefully you can. Let me. How do I? All right. So it's like 25K or so lines of code. Oh, right now I'm like, there's like stuff I haven't committed yet. So it used to be fewer lines, now it's a little more lines. But it's just basically no dependencies other than CUDA and other than a JSON library I'm using to parse some stuff. And then you can build it with make. So it builds in like a couple seconds. PyTorch builds in approximately an infinite amount of time. And then you can run it, you can give it like a model, you can ask it what is the meaning of life, and it outputs some results. The important problem in all of this stuff is, or there's like many important problems that are interesting to solve. So one problem with these language models is they're really, really big. I just yesterday implemented, there's like a sequence of steps that you go through. You start with a language model where every parameter is 2 bytes. 2 bytes doesn't seem like a lot of bytes, but when you have 7 billion parameters, and 7 billion is like the smaller ones, then you quickly start needing like gigabytes of memory. So I just yesterday started doing 8-bit quantization, or not quite quantization. There's a little bit more to improve there. I have a 16-bit version as well. Let me run this. So the 16-bit version is what I started with. It takes like 14 gigabytes of video memory to store parameters of the model. 14 gigabytes of video memory is like more than half of the video memory that my GPU has, which is fun. So the difficult thing about all of this is that there's just so much data, and to generate every new token, which is like a part of the word, like a few letters at a time, you have to read like the entire model. And this is a fundamental property of the way the architecture works. This is part of why I'm hoping that people will come up with some new architectures that don't require this, but we'll see. The issue with that is that reading 14 gigabytes of data takes time. And the amount of time that it takes is like clamped by the bandwidth, the theoretical bandwidth that your GPU runs at. So my GPU can read like a terabyte a second, which is a scary amount of bandwidth, as in like one thing you start to appreciate when looking like very, very closely into this is just how insane hardware has become over the last like decade or so. So a terabyte a second is insane. There's like 24 gigabytes of memory on this GPU, and it can read it at a terabyte per second, which by comparison, my current setup is there's like an AMD system, as in an AMD CPU, an AMD platform with like DDR5 memory. It's not the fastest memory, but it's like reasonably fast memory. And I think my CPU can read at most 40 something gigabytes per second, and 40 something gigabytes per second is still really, really, really fast. Because if I think back to, for example, I used to do a lot of low level programming in PlayStation 3 era before I joined Roblox. And there your ballpark was like 20 gigabytes a second, and that's like on the CPU. And that's if you were doing everything right. So like terabyte a second is insane, but the growth of hardware sort of is matched by the demands of software. And in this case, the time it takes you to read all of the model in memory or from memory for every single token you produce is like a problem from a performance perspective. So because of this, the biggest thing I'm doing sort of in general with this project is how fast can you run these models on a consumer GPU, which is what I have, assuming a single user, which is kind of what I am. So you have one thing that you're doing at a time. Your theoretical limit is the bandwidth. How close can you get to this limit? Usually this number is higher. Maybe the streaming actually interferes with this, which is interesting. I wouldn't have expected this to be the case. Let me run this again just to see. Yeah, so usually this, unless I broke something, which I don't think I did, is probably streaming. Usually this is 920 gigabytes a second, and this is like 860 or whatever. So this is close to the limit, but it is not at the limit. I don't think you can reach the limit, but as in no code I have ran, whether it was code written by me or code written by NVIDIA, which you would expect NVIDIA to produce the fastest possible performing code on a given GPU, but the fastest thing I ran was like 955 gigabytes a second or whatever on this GPU. So I suspect it might be the case that you can't actually reach on this specific GPU the full bandwidth, but maybe I'm wrong. I'm not fully reaching this, but yeah, so like I'm getting to 920. So the GPU is 4090. So the theoretical limit is like basically a terabyte a second, and the fastest thing I've seen running, like a single kernel, is 955, I believe. So this might be the real limit, I'm not sure. And then my current FP16 model code runs at 920, and then FP8 runs at, I think, at 860 or whatever. I just did FP8 yesterday, and there's more to go. Like it should be possible to get back to like 900 plus, I think, but we'll see. So yeah, this was a lot of fun, and this continues to be a lot of fun. I think I've been I've been doing this for a few weeks, and I expect to do this for a few more weeks because so FP8 is done, so that's cool. I have like a few things I need to do. I need smaller models, a smaller like weight footprint, so that I can fit even larger models, or so that smaller models can run more quickly. There is some stuff with parallelism where currently I am running the same version of code that's bandwidth bound always, but there's cases where you're not bandwidth bound necessarily. So I want to look into this, and there's some other stuff like this. So that's kind of cool. Somebody was asking, or somebody noticed that I'm running Ubuntu. Yeah, this is Ubuntu. I've been using Linux as my like basically dominant OS for work and for like non-work for a couple of years now. I think for a couple of years. I think since not 21, but maybe even since 21. Yeah, since 21. That checks out. The It's fine. So I kind of hate all operating systems equally, but I hate them for different reasons. Windows, I used to really like, and there were things that were nice about this. There were things that are not nice about this. They added WSL like years ago now, which allowed you to run like a Linux inside Windows environment that was very few compromises. You had slower access to file system, but it was like workable, and everything else was good. Since then, it feels like Windows has gone a little bit downhill. First, WSL is like not as good anymore because there is now two versions. The old one that was good, but they don't really work on improving it much. And the new one, WSL2, has horrendous I/O performance when you access Windows files. And so for me, this made it completely unworkable. And the other thing about all of this is it works for basic stuff like, oh, I just want to like run programs or develop some open source software or whatever. But then once you start needing access to the GPU, once you start needing access to performance counters, all of these things become more difficult. And then they get easier if you use WSL2, but WSL2 doesn't work fast or quickly with like Windows file system. Anyway, it's a disaster. And then now I have a Windows installed on this machine because like, I don't know, I occasionally play Windows only games. That's the only reason why it exists here. And it's just the OS is not pleasant to use anymore. Like you start OS, it prompts you with ads, it prompts you with like things that I'm not sure how to disable, like like I don't know, you haven't backed up your system in a while, like and then the update story is weird. So like a lot of things, so the WSL isn't as good. A lot of the things just don't seem like, I don't know. It's fine, like you can do work with the system, but it does feel like they're actively trying to make the OS be like a product and not like a tool. So that sucks. Linux is the opposite. Linux is like, it will get in your way when you do stuff because you will try to do something and it will not work, and you'll be like, how did this even happen? But it will not like be aggressively sort of I don't know, like asking you to fill a survey and like showing ads and like stuff like this. The other thing is that for the work that I'm doing now with CUDA and stuff like this, Linux is the OS that works best. Windows works kind of, but not as well. And then macOS, I kind of like in a lot of ways, but macOS since a few years ago started doing a lot of the like machine security stuff that really interferes actively with also like using the system. They don't do this in the Windows way. So Windows is like, oh, hey, here's an ad. macOS is like, there's no ad, but here's, you're like, you just compile the binary. We will like take a couple seconds to reach out to some server in the cloud to check if your binary is good or not, because there is like it's supposed to have a signature, whatever. And then like sometimes like, oh, your process doesn't have a signature, so we're gonna like kill the process. And it's fine from a certain perspective, like through a certain lens I can see why this is valuable, but for me, like for an expert user, it really interferes with like actually working. So anyway, long story short is, yeah, I've been using, oh, and it is Ubuntu. I've used like other distros like 20 years ago, but I think since 15 years ago, so like anytime I actually ran Linux, it was just Ubuntu. It's fine. I'm just used to how it works. I'm used to the package manager, etc. Like it's just no surprises, minimal surprises. Things mostly work, stuff like that. So I don't know. It's okay. But yeah, somehow we ended in the state where like uh, for me, the year of Linux desktop is now. Uh, Not because Linux desktop grew like super good. It actually didn't. I can talk a little bit about this, but everything else is just not good either, which is a depressing state of affairs. The Oh wow, there's a lot of stuff in chat. Let's see. So hi Becca. Uh, Yeah, so let's see. JSON dependency. So it's kind of funny. I have all of this code that's doing all of this difficult stuff, and then I have to parse JSON, and then this is the only thing that I just didn't hand code. And it's like a 400 line C library. I feel like I can do 100 to 200 lines of JSON parsing maybe, if I try hard enough, and that will like make. I actually plan to remove the. I have the in my README. It says minimal implementation and minimal dependencies. So and I don't know if you can read it, but you need a CUDA run. Like I'm not gonna re-implement. You can't even re-implement parts of CUDA like physically, but like obviously I'm just not gonna do this. It's kind of like a computing platform at this point, right? It's like you don't write a custom C compiler, you don't write a custom CUDA compiler. It's fine. I do take a point. CUDA, the way NVIDIA software stack works is it's like good. It's just not. Parts of it kind of defeat some of the point of why I'm doing this, because the way CUDA works is there is like a CUDA driver, and then there is the compiler, and then there is a runtime. My handwriting is great. You can tell I'm practicing my handwriting. So they're like depend on each other, but like these kind of are your fundamentals. You just can't really work without them. You can sort of get around without a compiler if you write like assembly by hand, but that's not the route that I'm taking. You'd have to like pay me for this. And I'm just doing this on my own time, so that's fine. But then CUDA has a bunch of helper libraries, and to some extent they're not even. I don't know if helper is the right word because they're doing fundamental stuff that it's like difficult to get by without. So there is a BLAS library. BLAS stands for basic linear algebra. I don't know what B stands for. I don't know what S stands for, but linear algebra is there somewhere. This is the library that implements like matrix multiplication, matrix vector multiplication, and then like 75 variants of this, right? And then there's a bunch of other stuff. There's like DNN library for some specific like neural network related operations. There's like an FFT library for people who need FFT, which I don't. There is I don't know, there's like tensor and Cutlass, which is anyway, there's like 20 or so libraries on top of CUDA, but you don't need them in the same way that you need the CUDA driver compiler runtime, because you can write CUDA code that implements the same algorithms or sometimes different algorithms on top of the same foundation. So I'm taking the route that says I don't use any helper libraries. I need to write everything myself, other than the CUDA driver, which I'm not going to write myself. So that's my dependency that's not sort of negotiable. But then the one dependency that is negotiable is that I'm using GSMN, which is like a JSON parser. It's a nice library. It's C only. This whole project is in C. It's nice, but I might just not need it. I need to parse like I don't know, the way I'm using like a model format that is a giant binary file, and then most of this file is like the actual numbers. But in the beginning of this file, there is a metadata section where it says, oh, hey, here's the parameters, here's how big these matrices are, here's where they're stored in the file, etc. And this thing could have been binary, but this thing is JSON, and it's fine. It's actually like, I think, a good format design. If you look at GLTF, for example, GLTF files, GLB files are the same way. There's like a binary file, there's a hopefully small JSON part, and then a large binary part. So yeah, I don't know if I need like a 400-line library to parse like 32 kilobytes of JSON with a fairly constrained format. So I might get rid of this in the future, we'll see. I'm kind of, parts of this project are pursuit of minimalism for a deep fundamental reason. Removing the JSON library is not going to be pursuit of minimalism for a deep fundamental reason, but I still might do this because why not? It's fun. Anyway, so let me go back and catch up. Implement LM inference from scratch. So hold on. Okay, hopefully the stream is back. Let me see. I can try, hold on, let me, fine. Okay, I think we might be back. Can somebody, okay. So this serves me right, I guess. I have like a Wi-Fi mesh that I sometimes am using and sometimes I'm not using, and I guess it's a bad idea to use it. But okay, I think we are back. At least the pings are back. The stream date is back. Okay, let's try to get back on track. Sorry about the connection issues. Unexpected. Even though I should let me just keep running ping here, and then I can refer back to this to check if the connectivity works. Okay, so sorry, let me go through the chat. So so LM inference from scratch, there's Andrei Karpathy's series. It's written in Python. You can go from this to C with no issues. And the one thing I wanted to mention is the way I started this project is actually Andrei Karpathy has a really good C implementation, but this is CPU only. It doesn't try to push performance, and I've been rewriting like portions of this as I go, but essentially I started from, he has this like 1,000 line long C file, doesn't have a JSON parser because he's using like a custom binary format and stuff. So this has been helpful because I think in general the way I like to write code is that I like to start with a working version and then always have a working version, as opposed to spend like weeks in the state where nothing actually works end to end. So this has been very helpful. But yeah, I rewrote like 70% maybe of this code by now, but in fact one of the diffs that I had, like the thing that I haven't committed here, is me rewriting like not the last 10%, but like the half of the remaining code, because he had some like quadratic algorithms there which are fine for the demonstrative purposes, but I'm starting to run into the performance issues there. So anyway, so yeah, I know. So I'm sure the fact that Canonical is running Ubuntu is in some sense like against the spirit of Linux. Like they have to make a profit somehow, right? But again, so it works fine for me. The only thing I'll say about Ubuntu is sometimes I wish their packaging story was a little cleaner around newer versions of software. I often run into things where like, oh, I need the latest Clang, and like there's no package for latest Clang in the official repositories, and then you have to like add custom sources, and sometimes things break. I had this like insane set of issues around CUDA installations earlier this year. I think they fixed a lot of this now because they're using a cleaner like CUDA packaging since I think the latest version of Ubuntu, like the latest point release. But anyway, I understand why people don't like Ubuntu in this community. I think for me it's like my goal is minimum amount of configuration, get to a working system, get to a stable system, and then keep it this way. And Ubuntu is fine for this for me. And yeah, all right, sorry, there was a okay. So ballpark perf comparison for between what I'm working on and what other people are doing. So this is a good question. The answer is, when I started this, I wasn't sure how far people push things in this space. The answer seems to be that depending on the project that you take, you might either see the project that runs at the same performance, or the code that I'm writing might be 10 to 20% faster. It depends. I was looking at this recently. So these numbers again are impacted by streaming. This is like nine should be 920 or whatever. Or the other way to look at this is like this number, which is how many tokens you can output per second. The most how do I phrase this? So the only implementation that I know of that doesn't have this crazy Python, PyTorch, etc. dependencies is llama.cpp. My code is faster than llama.cpp. So that is good news. Faster by 10 to 20%, depending on the model size. I'm hoping to get it a little faster still, but it's understandable why they're building something much more general. I'm not like super interested in doing that. So we'll see how far I can push it. But yeah, the delta isn't that large. If you compare to some PyTorch-based versions, then it depends. There is PyTorch-based versions that have a lot of custom CUDA code written for them that basically match the speed that I'm getting to here. There are versions that I used to think were fast, but they're not that fast actually. So let me see if I can. Let me try. So there's this thing called GPT Fast, which is a recent PyTorch thing. PyTorch in general isn't like super beating efficiency records, but they recently released this thing called GPT Fast. Oh, I don't want to run GPT Fast right now on stream because I tried this yesterday and it worked, but it was given. I messed up something with the installation of local Python packages. I'm not sure. Let me run llama cpp instead. It's gonna be a little different, but let me see. So for fun, I just implemented 8-bit yesterday. It's not like there's ways to go there still, but let's just run. Oh, sorry, this is CPU. Let me run the 8-bit version there, just to give you like an idea. So you want ideally, no, I want, hold on. Okay, whatever. So I'm getting about 94 tokens per second with llama cpp, and I'm getting about 115 tokens. I don't know if both implementations are impacted the same way by the stream, so I'm not sure if yeah, I think the numbers track. So 115 over 93. Oh, uh, so this is like 20% faster. Um, uh, so this might not be network based then. Lesson learned. Okay, this is gonna be a wild stream. Basically, I think the rule is don't. Oh, probably when you run a workload like this, it just takes out. This is odd. Anyway, I will not run anything CUDA related again on the stream. But the upshot is I'm around 20% fast right now. I'm hoping it's gonna be a bit more. My goal is not to beat. My goal here is not to produce like a practically useful piece of software. You can think about this project similar to my previous project Niagara, which I did on stream. I'm not doing this one on stream. But the goal is similar. The goal is to explore the space. The goal is education. I will probably run or write some posts about this once I get to like better results, even better results, stuff like this. But yeah, but again, like if you're interested in production use cases, there are some Python-based packages there where if you forget about the minimalism and stack depth issues and stuff like this, then they're fine. They're gonna run as fast or faster in some cases. All right. Windows. Yeah, the fact that Windows also installs Candy Crush. Maybe this is when it started, because I think they started preloading Candy Crush and like all of this stuff in Windows 10 days. Maybe this is when the descent or the decline started. Anyway, so without CUDA, well, I have a CPU version. I don't really care. I think if you're doing inference on CPU, then Llama CPP is basically great. You can like, it's gonna be hard to beat it realistically, and like I don't. Writing fast CPU code is something I can't be. How do I put this? There's no real education value for me myself in like writing the fastest CPU implementation. Like I know how to do this. It's not super interesting. One big attraction for me in this project has been exploring CUDA on like a fairly deep level. So that's cool. Having said this, I do want to get to the point where I can run this project on AMD hardware. It is doable. I don't have an AMD GPU, so I'll need to buy an AMD GPU. But once I buy an AMD GPU, once I obtain an AMD GPU somehow, then I kind of want to try, because AMD GPUs should be reasonably well sort of structured for this kind of workload. There is software issues on AMD side, so I don't know how much I want to do this. I don't want to like rewrite the whole thing in Vulkan or whatever. And if you are doing CUDA like essentially compute, then there's software issues on AMD side. So I'm not sure if I want to go there, but maybe I will. We'll see. All right. Sorry, let me reorient. Okay. Yeah, I ask OneDrive on Linux. It's fine. I don't really have opinions on Bifront. It's fine. I don't know. Okay, so stream died. Critical bit flip. Oh yeah. I let me talk about hardware stuff. It's kind of funny. So yeah, the hardware journey was interesting because apparently, well, it's kind of not surprising, but I didn't. When you work with graphics, you have different expectations. So you work with graphics, you have the goal of your application is to produce pixels on screen, right? Fundamentally, your expectations then are there's other things that produce pixels on screen. You might run in full screen mode, in which case, hopefully, nobody else is producing pixels on screen. But if you run in windowed mode, there is all of the other applications that produce pixels on screen. There's also the compositor, right? So if you run in windowed mode, there's like the window that you are drawing into. You have like a Vulkan context or whatever. But then there is a bunch of other applications rendering stuff around you. Then there is the compositor that takes all of these individual bits of data, assembles like a full frame of pixels, and then essentially sends it via scan out to the monitor. In this world, there's a few things that are kind of different from what you need for all of this CUDA-based compute, or not different in the sense like your expectations are different. So your expectations are every 16 milliseconds or so, or maybe this is actually 144 hertz monitor, so like 7 milliseconds or whatever. There's going to be like an effort, a collective effort to produce pixels on screen, right? So there's going to be the compositor, is going to hijack whatever is running right now. If your application right now is doing work on the GPU and the compositor really needs to present the screen, it's going to present stuff to screen, which might intercept whatever you're doing via like a GPU context switch or whatever. And it's just how it is. Like fundamentally, if you're rendering stuff for graphics to display on screen, and if you are interfering with the presentation process, then you have lost your opportunity to present stuff on screen, so you shouldn't be doing this, right? So, and then if you think about, how is GPU memory used, then of course, different applications have different buffers stored in the GPU memory because they all want to also present stuff to screen. When you are in the process of like, when you have 16 milliseconds of work or whatever it ends up being for these larger models. So for the FP1, it's like 8 milliseconds of work, which is also actually larger. So for 144 hertz display, the time it takes me to infer a token right now with the smaller models is larger than the presentation interval. This means that there is a virtual guarantee that if the GPU is actually used for rendering stuff to the screen, then at some point during me like doing this hard work to compute the token, there's going to be an interrupt on the GPU where some other apps will do some other graphics work to like actually show stuff to the screen, which is fine, but this impacts my performance numbers. It also impacts my performance numbers unpredictably because there is sometimes the context switch might happen, sometimes it won't. In this case, it's usually one-to-one, but you might have the weird one-off case that will happen, like statistically speaking, relatively often, where so you have so this is let's call it 9 milliseconds of work. And let's say the refresh interval is 7 milliseconds, there is going to be a case where you get interrupted twice, at the beginning and at the end, because it will just so happen that the work that you're doing will line up with the VBlank, etc. in this way. So there's going to be cases where your performance is impacted more or less, etc. So anyway, the long story of all of this is, and also it turns out that Chrome and Windows system, etc., consume like gigabytes of memory, of video memory on a 4K screen, at least on Linux. I haven't checked on Windows. Turns out, if you plug your monitor into your onboard graphics card, that now is a thing on AMD as well, because AMD finally started shipping CPUs that have integrated GPUs, which sounds like a weird idea for a gaming setup, but it's actually a really, really great idea for many non-gaming setups. So it turns out all of these problems disappear. So this is how I'm running my system now. I have two GPUs. The monitor is presenting from the AMD GPU, which is the integrated one, and then the NVIDIA GPU is basically only used for CUDA. I don't really play games that much on PC. I play all of my games on PlayStation. And so like it's fine. It's working well in this setup. It took me some time to get to the setup, and the whole GPU journey was a little bit crazy. I missed the window. I should have built an UPC like earlier this year. GPUs were still easy to get, but now like there's this AI craze, I guess. I don't think people are mining anymore, but I think everybody wants a 4090 because it's like if you want to build an ML server in your garage, then going for multiple 4090s is like not the worst option. And so I think because of this and because of some China issues and stuff like this, like 4090s have just been a struggle. Every single car that you buy, I think, is aftermarket is not the right word, but basically it's like scalped. Somebody buys this and then resells it. So I ended up spending like way too much on this one GPU, but I could have bought the same GPU like for way cheaper earlier in the year. Anyway, so that's a little annoying. This is unfortunately sort of the reality because so AMD cards are easy to get, but the software I heard isn't great, and everything that's not a 4090 has less than 24 gigabytes of VRAM. And VRAM is like the real priority in all of these cases. Even if you're not doing LLM work, when I was doing my ML like courses and stuff like this early this year, I had a 4070 with 12 gigs of RAM, VRAM, and then a couple of these gigabytes are taken by the windowing system, and so you get like 7, maybe 8. 7 is on the low side. You could get up to like 9 gigabytes of actual data and you'll be fine. Even though I wasn't really working with LLMs at this time, I would regularly run into issues where my models just don't fit because during training your memory requirements are substantially larger, and you can work around all of these issues. Like people figured out how to do like model sharding and whatever. Like it's fine, you can figure it out, but the software setup is much more complicated and the training is slower and stuff like this. And so like you really want the maximum amount of video memory that you can get, and maximum video memory that you can get with the 49 with the regular consumer card is 24 gigabytes. So it's kind of what it is. Yeah, the troubleshooting aspect of the graphics from motherboard is also super great. Like, so this is a new, how do you do this? I forget. LS CPU does something else, I think. But anyway, so like yeah, I built a system a couple months ago with like 7950X, and then I have some obscene amount of memory, like 192 gigabytes, and so yeah, it's like a brand new system, basically, and it is a relief for you to be able to start the system without a graphics card and then figure out the graphics card situation separately. In fact, I think I spent a month or so with the system without a graphics card at all. Obviously, I wasn't doing like CUDA stuff, but yeah, it's been fine. So yeah, so that's what I've been doing for the last few weeks. So yeah, I have some plans for kind of where to take this project further. But again, I think you have to. The reason why I'm doing this is not to make a piece of software that other people will necessarily use. However, it might be useful in indirect. It's definitely helping me orient myself in this space. It's definitely interesting work in general. It kind of takes only the good parts from ML, removes all the bad parts from ML that I don't like personally, and this makes it the optimal way for me to experience ML in this like sort of not really production setting. There's a lot of ways in which this is sort of divorced from the production setup. Um, in a production setup in general, you don't want to be bandwidth bound. Like bandwidth bound is a bad time. You ideally want to have so much work to do that you become compute bound. And the way you get so much work to do that you become compute bound is by doing a lot of things at once. And the way you get to do a lot of things at once is by running like a production system that serves many requests at once. And so once you're in that zone, then the work that I'm doing, you can still do this work, but you do it differently. And like some people are doing this. NVIDIA has some libraries that are like basically dedicated to this library called Faster Transformer, which I think this whole purpose is you're running a production system with PyTorch, which I'm not sure if you are, and you want to achieve the maximum possible sort of throughput of the system, assuming that you have a very long incoming queue of requests, or like a never draining queue of incoming requests. Like you always have more work to do than you have time to do it, type of thing. And in this scenario, with these models, you become compute bound if you've written everything super carefully. In some parts of the pipeline, I don't think you become like it's complicated. These architectures are in many ways not super optimal for the GPUs. There is this general issue which graphics has been doing fine with, but ML is changing a little bit the structure. So I'm kind of wondering to what extent people will take this into account. In graphics, or in GPUs I should say, there's this, you might have seen these graphs where there's like the growth of the bandwidth and then the growth of compute. And the growth of compute is like way outpaces the memory bandwidth. It's slightly different from this, but one thing that a lot of graphics programmers would have seen is this quote unquote ALU text ratio. It's not exactly the same thing, but it's kind of very similar. ALU text ratio is also dependent basically on like special purpose computational units on your GPU, not just the bandwidth that you get. But this is kind of if you worked in graphics like 15 years ago, then you would spend a lot of time trying to do with absolutely bare minimum amount of compute. Like your shading formulas and BRDFs and whatever would be like, here's like 7 multiplications that we can afford, and like that's it, and we are gonna fetch like 2 textures. And now it's like, okay, yeah, sure, we're gonna fetch like 10 textures, but also here's like 4,000 LU operations that we're gonna do for this. And it's fine because the ratios are like large now. I'm not sure what they are off the top of my head, but like 100 to 1, I don't know. The ratio of flops to bandwidth, I think, is like 1,000 to 1. Depending on how you count flops, depending on how you count bandwidth, depending on a lot of things. But these ratios are very large. In ML, it is weird because in ML, if you took the problem like if you took a theoretical kind of view at the problem, then your main especially for the problem like this, so for the problem that I'm solving, the main computational primitive is like this. You have a matrix, you multiply it by the vector, you get a vector. To produce this, you have to read every element of the matrix on the left once, and then do like 1-2 flops, depending on how you count flops. Do like 1 multiply add operation on it. That's it. This is why this is bandwidth bound, because there is so much LU that you are never gonna run into an LU limit unless you do something. You can like use the GPU inefficiently to not reach the peak bandwidth, but it's hard to actually hit the LU limit. You're just gonna hit some other limit if you do this, because the problem is so lopsided, right? It would be nice if instead what happened is, I don't know, here's like 16 floats here, and then we are gonna do some really, really, really complex function um, that takes the 16 floats and then takes like, I don't know, 4 floats here, and then produces 4 output floats, but not like in 16 flops or 32 flops or whatever, but like with 1600 flops. Because the function is so complicated to compute, it just requires a lot of math. But this is not how the systems work. So if you have a lot of vectors that you need to transform by a single large matrix, then things become different and difficult because the balance shifts more and more towards flops, and you can be compute bound. If both matrices are large enough, you can become compute bound. This is part of why NVIDIA has been investing heavily in specialized ML extension storage hardware. Like they have all of these like Tensor Core stuff. This is kind of why it exists, because you actually do become compute bound. But for a problem that I'm solving, like you don't get compute bound. The reason I forget how I came to this topic actually. But what? Oh, right. So the reason why this is important is that this is how you are thinking of the production systems for this field. You have to have a lot of inputs. Once you get a lot of inputs, instead of this situation, you get like this situation, and then you start becoming compute bound. And you want to be compute bound because your compute is so much more plentiful on this GPU hardware that you're not like using the system efficiently, essentially. So I think the claim that you can make definitely about my current project is that it's not actually using the GPU system efficiently. It's maximizing the single component bandwidth, but the compute efficiency is actually terrible. If you were to try to maximize compute efficiency instead, and bandwidth at the same time, ideally, then you could actually use the GPU at its full capacity. The problem is the way these models work for a single user case, you can't do this. It's just like not how the system works. So it's kind of the best that is possible given the situation at hand. Let me see if I missed something from earlier, because I feel like, oh yeah, I think somebody was asking about I forget. I think there was a question about like game development for Windows. So I no longer work at Roblox, so I no longer do game development. But while I worked at Roblox in the last couple of years, I've been mostly using my Linux system, but I've mostly not been working on graphics. Mm, the production servers that Roblox run are obviously on Linux. So like there is a large portion of the work that is very meaningful, and I would use macOS as well. So I would be using like Linux, macOS, and then occasionally Windows, but not super frequently. But yeah, game development on Linux, it depends. My understanding is that both Unity and Unreal are still in like half support mode. Um, as in, I forget, the editor works, but the player doesn't. Maybe on both, maybe on one of them, I forget. It's a little weird. Having said this, I think if you're doing Linux, if you're doing game development using like open source stacks, for example, then it's fine. I mean, I ran Godot on Linux. Godot runs fine. Vulkan runs very well on Linux. In fact, Vulkan, in some sense, runs better on Linux. I talked about this before, but on Linux, on AMD hardware, and also on Intel hardware, but most importantly on AMD hardware, you can like compile a driver from source. You can even compile a driver from source that's like super close to the AMD's official open source driver, which is MDVLK. So on Linux, there's like multiple MD drivers. The main ones are RADV um, and MDVLK. I'm talking about Vulkan drivers, like if you use OpenGL, God help you. MDVLK, as far as I know, is like fairly close to the version of the Windows Vulkan driver that AMD ships on Windows. RADV isn't, it's completely separate code base, but RADV is interestingly what Steam Deck uses. So even if you're running, like you're often running Windows games on Steam Deck, they go through these layers of emulation, but they terminate from the graphics perspective at RADV, which is the Vulkan graphics driver, which you can just use. So both of these drivers are open source. RADV is nicer in my opinion. It's a smaller code base. It's very easy to build. It's part of Mesa. It's fast to build, and the code is very easy to read. And this is nice if you're doing low-level graphics development, because this gives you an opportunity to really introspect the work that the driver has to do on your behalf, and then figure out, have a better understanding of how the hardware works and what you can do with this and stuff like this. There is a way in which RADV is less nice, in that AMD publishes or releases really, really good profiling tools, for, like Radeon Graphics Profiler, and then some second one, I forget how it's called. I think neither of them work with RADV, or maybe there's a way to make them work with RADV, but it's like sketchy and not all of the features work or whatever. I don't even know if both of them are fully functional Linux, but essentially you are missing out on like good tooling. But you get good source that you can change, and I don't know. Both are valuable in different contexts. But especially if you can get RGB and stuff to run on Linux with the official AMD driver without compromises, then like there's nothing fundamentally wrong about sort of Linux game development. Except that, of course, you know, like if you're doing game development for multiple platforms, your main platform of choice is Windows. Your second set of platforms of choice is either mobile or consoles. Console tool chains, I don't even know if anything works on Linux. You don't want to be doing this. You want to go from Windows. If you're targeting mobile, if you're targeting Apple, then you have to start from Mac, right? So like neither Linux nor Windows work. If you're doing Android, then either Windows or Linux or Mac will work. So yeah, like if people who work at Roblox, for example, or people who work at like large AAA studios, they mostly don't use Linux, and it's like very understandable as to why. So yeah, that's a little bit unfortunate, but I mean, I think the whole game development on Linux and game industry on Linux story is like lackluster in certain respects. So I think it's like not surprising, particularly. Okay, more people wrote stuff. Do I see WoW making its way into Fortnite? No. Epic Games already has language called Verse, and still I'm starting WoW in some games. I don't think so. I could. You can integrate WoW into anything. Somebody noted Alan Wake 2 is using WoW, which is awesome. Alan Wake is using a custom engine, Northlight, I think it's called. Warframe is using WoW. Warframe, I believe, is also a custom engine. Warframe used to use Lua before, so this is an example of Lua like as an upgrade from Lua, which is super nice. My understanding, I think there's an article on Remedy's blog somewhere about Northlight, and it mentions Lua, and I think they say that essentially they didn't use Lua, but they replaced like a more basic sort of in-house scripting language with it. So there's no reason. I talked to people who use Luau in Unity, which is fun. So there is no reason why you can't integrate Luau into Unreal or into a project that Unreal uses. I think the chances of Epic integrating Luau are zero as far as I'm concerned. Epic has had Unreal Script. And then they had like what feels like a decade, maybe that's less, of time without a scripting language at all. They have Blueprints, which is a visual scripting language, and now they're building Verse, right? In this span of time, they could have done anything else. They could have integrated Lua. They could have integrated Luau in the last 2 years. They could have integrated JavaScript. Like I don't know. They acquired a company that builds CuckooScript. So they could have like integrated that or built something. Anyway, like none of these things happened. They're building Verse. It's fine. Well, I disagree with some of their decisions, but like they can do whatever they want. I would also say in general, Unreal is not. It feels fairly rare for Unreal to use open source software. It's not quite right. Of course, they use a lot of open source software, but it feels that given a random problem, it feels that they're more like, I think they have a custom XML parser. I'm sure they have a custom JSON parser. Maybe they integrate it. I think they have a custom XML parser at least. Which sort of makes sense on some level, and especially for a scripting language. I mean, I understand why they wouldn't do that, but it's whatever. Like it's their own company to run. They can do whatever they want. I'm not sure I would be making the same decisions, but I'm not making any decisions there, so it's fine. But yeah, no, I don't think this will happen. They started build. This was a possibility before they started building Verse. Now that they're building Verse, essentially, it's very clear that they are going for the world where there is C++, Blueprints, and Verse. Verse, I think, isn't available still in Unreal, like outside of Fortnite, but I mean, I'm sure at some point it will be. I think it's on their roadmap. I don't think Unreal has any plans to do C# either. No, I think it's gonna be C++, Verse, and Blueprints. And like, if you are running an Unreal project, you can integrate anything else because you have the source. It's probably not that difficult. But then you're missing. Maybe you're missing out. I don't know. Like, I'm sure that it's kind of the same story with Roblox in the sense that a lot of the work in Roblox of developing languages isn't just the language itself, it's how it integrates into the rest of the system. If you are taking Lua and integrating this into Unreal, then you're gonna have to do this work. This is work that you have to do for any language. It's just that in Unreal's case, eventually Epic will have done the work of doing this for Verse. Again, right now, Verse, I think, is still not available in Unreal project, so you're expecting them to eventually get to this, which I think eventually they will. It's just a question of time. So having said this, it's Verse is interesting. The current implementation of Verse, my understanding, is extremely non-competitive, but my understanding is that they're gonna make an implementation that is hopefully competitive. I don't know. I don't really know what their plans are. Anyway, yeah, I have mixed feelings on this whole Verse situation, but I will probably not go into this. So Rad was on par with proprietary drivers with profiling. Okay, that is interesting. Yeah, I remember. I guess last time I tried this, I think the issue was not even Rad. I think the issue was Rad as well. Last time I tried this, I was working on Niagara and I needed mesh shader support, and I think I hit the issue from both sides. I think RGP didn't yet have mesh shader support, but also the Rad thing that captures the trace for RGP also didn't have mesh shader support. So neither side be willing to connect to the other for this particular subset. But yeah, like if you're not doing mesh shaders, then maybe it's fine. I haven't really honestly used AMD tools on Linux like ever. I should say, by the way, CUDA tools are fairly good for compute profiling. I've been using Compute Nsight systems. There's like some issues with them, but like they're largely fine. NVIDIA's Linux situation is kind of hilarious. For example, there's this thing called Nsight. So I don't know if you can tell. I don't know if the cursor is right now like streaming. I'm hoping it is. I don't know if you can tell that it's substantially larger than the normal cursor. And also, I don't know if you can tell that there's no window title. Like I can't, this is not a window I can drag. I can quit the tool, thankfully, but I can't. Let me see, I don't wanna like run anything. I guess I erased. I don't want to run this because I'm worried about the stream health when I'm running these workloads live, but I could, maybe I should risk it. Maybe I should risk it. There's a chance the stream will explode right now. Let me think about if I want to risk it, but yeah, so the window header thing is hilarious because so this system is running Wayland now. When I was using NVIDIA, I was running X, and NVIDIA's Wayland situation is like extremely weird because basically it kind of works, but then there's a bunch of basic features that are missing. And then it looks apparently like the NVIDIA tools nobody has ever ran on Wayland either, because on X the title bar is there, and then on Wayland you have to do something special, I think, to get the native title bar back or whatever, and I guess I'm not doing this, I don't know. Whatever. Point is, yeah, there's like the tool is nice, but you can't drag the window, which is a little annoying. But the functionality of the tools is pretty solid. You can do sampling profiling. You can't with this specific tool. This is a system-wide tracer, so it can sort of do this, but I don't think I've seen it work well. You can't inspect the kernel and ask like very deep questions about the specific kernel, but you can do a very good system-wide trace and look at what you can look at like performance counters that matter at individual sort of time steps and stuff like this. So you can say, okay, while my code is doing this in general, I'm hitting this kind of cache utilization, or this kind of bandwidth, of this kind of compute efficiency, and this can help you optimize things. So it's fine. There's a second tool that I used a little bit, but not as much, which focuses on single kernel profiling, which is a little bit flakier, I would say. This tool has been super rock solid and useful. The other tool has been not useful yet, but also kind of flaky. So I don't know. But I think for deep performance analysis, you kind of have to use both. So I decided I do not want to risk this. It's unfortunate that I don't have files saved, but anyway, it's a nice profiler. This is part of why if I were to get an AMD GPU and do the same work on AMD, like I think the AMD compute tools are not going to be nearly as good. What advice would you give to graphics programmers beginner? I wrote small 3D render in Vulkan. Apply. So I get this question occasionally. I don't have great insights into this, in the sense that I know what is interesting for employers to ask about. I spent some time, it was a while now, but a while back I was interviewing basically every Roblox rendering candidate. This hasn't been the case for the last like 4 years or whatever. I don't know what people ask these days, but I know what people want. The thing I don't know is this. I myself went through the complex process of like sort of education and working on projects and stuff like this that took a long time. And this is the only real frame of reference that I have from the point of view of how do you get to the knowledge, right? And this was long ago that I don't think it's even a good idea to repeat this. I'm sure there's more efficient ways. So I don't really know like super well. I can say a couple things. So one is hands-on experience with um, graphics APIs and basically doing the graphics work yourself, not just doing this sort of inside Unity or something like this, is like super valuable. So that's number one. Number two, it is nice to have had the opportunity to work with an engine that is not of your own making. It's used to be very difficult to get into this, but today I would ask questions like this. For example, maybe it's worth the time to look at contributing something to an open source engine. For example, Godot is a big C++ engine in open source world. Bevy is a big Rust engine in the open source world. Maybe it's a good productive use of your time to spend like a few weeks improving something there, submitting a pull request, that kind of stuff. Um, and like understanding how these engines work is good as well. So then beyond the APIs and stuff like this classic advice I think is read a few papers and implement them. If you have written your own renderer in Vulkan, then you might have already done this. If you haven't, you should. Basic things like get a PBR set up with like HDR, shadow mapping, a couple post effects, maybe something like separate, specialized like water shading or deformation or something like this. Implement a couple, look at SIGGRAPH 2020 or SIGGRAPH 2019 or something like this and implement something from there. Some of this work may be really difficult to kind of implement as a hobbyist because like maybe it requires art assets in the type that you just don't have access to. Maybe it's just like it took that team a year to build the technique, so they are sharing their results, but like you can't replicate this in less than a year. Some work is definitely replicable. One basic example is that one of the inspirations for my Future is Bright project, which was done in a week on Hack Week. Obviously, I knew what I was doing, but like still it was done in a week on Hack Week. One of the inspirations was the Doom renderer, the Doom 2016 renderer, I think, and that's like I think that's like a SIGGRAPH 2016 or something. Like there is a paper on one of the conferences that came out, and like you can implement the whole thing. It's fine. So that is valuable. One really valuable thing that's really difficult to get is trying to get an insight into how the GPUs actually work. I can highly recommend Fabian Gizen's series on graphics pipeline. A trip through the graphics pipeline 2011. This obviously came out in 2011. It's been 10 years since. However, a lot of the stuff still holds to a surprising degree, and two, the biggest important thing is not just having the knowledge, but like sort of. It doesn't matter as much if you know exactly how the GPU that you happens to be using, like what's the exact implementation for, like, I don't know, LU, like command distribution or whatever, LU like instruction scheduling. Like the most important thing isn't that. It's that you have a general understanding of how these things can work and how they're different from what naive implementation is, or sometimes there's not even a naive implementation necessarily. One, I don't think this is an interview question anymore. If it is, I think Angelo wrote about this on his blog, so it's probably fine. But it's like a popular question that people ask, for example, in interviews is, how does MIP mapping work? Why is MIP mapping useful and how does it work? And why is MIP mapping useful has a basic, simple answer that is easy to get to yourself if you just use the graphics API. Like you disable MIP mapping, you see that you see shimmering artifacts. There's like correct scientific explanations for all of this that are difficult to derive on your own, but like the basic mechanics are very easy to get to. Then it's like, okay, you enable mip mapping and fix this, then you look at the texture format or something, and it's like, oh cool, it has these mip levels that are like halving in size on every step. And like, so the basic structure from this perspective is very, very easy to understand, even from ground zero, even if you just look. If you ask yourself how is the MIP level computed when sampling a texture, this is a little bit more nuanced, because you can introspect this question all the way down, as in there's like a 5 whys technique or whatever. You can ask a 5, maybe it's not whys, but like you can ask questions about how it's implemented, and then if you come up with an answer, you can ask, does it really work this way, and does it conflict with some other stuff that we know to be true? And you can get to an interesting it's a worthwhile sort of series of questions to ask yourself. Do I know how a thing works? And if I try to figure out how a thing works, how would I do this, and like what's my answer? And then can you compare this answer to like the reality and figure out where the mismatch is? But mip mapping specifically, I think, is one where the answer is not obvious to some people who haven't like looked very, very closely at this. And this series is not about this, but it's about things like this. So this is good. So implemented papers, so I think this is, and I guess experience using performance profiling tools is also, it can teach you a lot, because again, I think the most important thing is basically how do you connect, how does hardware actually works with like what's the very, very high level intent is, and how many pieces between these two can you fill. And so implementing papers, read this thing, contribute to some open source engines, writing your own engine, like super good, super valuable. Implement a few algorithms in either your own engine or a third-party engine. Yeah, I don't know if I have more interesting advice than this. I think fundamentally a lot of this stuff comes with experience, and so a lot of this has to be you work on like actual tangible problems and then see where it leads you. Okay. Yeah, I have. Verse has issues. Verse has, I think the language itself, for every decision in Verse, I understand why it was made, and I could maybe argue for it, and it's an interesting path to take. It's just that I think there are so many downsides to some of the specific choices, and a lot of them are because of time it takes to develop this. And this is part of why. Essentially, Verse is like very interesting, but it's kind of this. I don't want to belabor on this too much. I haven't really talked to people who work on Verse a lot. I've mostly followed this externally. It's just that I think essentially. On one hand, I can argue for every decision, probably for most decisions, not for every decision, that Verse is making. On the other hand, I keep asking myself the question, if they made the decisions very, very differently, would they be in a better state now? And I'm not sure what the answer is. So it's kind of a long-term, short-term thing, but the issue with the long-term angle is that really they've been doing this for a while, as far as I can tell, as in they killed Unreal Script and they worked on blueprints, and then they acquired this company, like, it took a while to get to Verse, is what I'm saying. And it will take a while before Verse is like a full-fledged citizen of the Unreal ecosystem, available in Unreal games, has excellent performance, has excellent tooling, yada yada. It's come pretty far for a very young language, but it has a lot more to go. So anyway, what advice would I give to a small company writing their own engine from scratch? Don't. engine landscape is getting really weird now. I've thought about this a little bit in the past. Definitely this year there was this rude awakening for people who use Unity. But really, I think if you've been following along with Unity for a while, then it feels to me like for a while now, it felt to me like the company has lost its ways a little bit. Not in a super fundamental sense, but uh, I don't know if it was ever true that you could like that Unity was the for a subset for a specific subset, etc. It was like the perfect technology or whatever. But I think there was a period of time where it felt like the goals of Unity are very closely aligned with the goals of people who work with the needs of people who work with Unity as the engine. And then for a period of time, it felt like this disarray where I wasn't even sure what the goals are anymore of the Unity engine, but you looked at the actual sort of things that are being shipped, things that are being worked on, and it was just a little bit odd. I don't know. Some of this is covered by kind of my background and experience, and like different people make different decisions, and many times it's actually fine. But for example, Unity has spent years now, as far as I can tell, in the state where there is too many renders and neither is good enough. I think this is changing now, or maybe it's going to change next year. I watched the Unite presentation, and it made me a little bit more hopeful for the future there. But for a while it was weird. Like, here's the old renderer that has been production proven, doesn't have a lot of good things that people expect by now. Here's like two new ones, and one doesn't have the features, and another one isn't practical to run anywhere, or not anywhere, but like very very small subset. And then there was a lot of incompatibilities between them. And then I don't know, I heard stories about like people painfully reworking their game to work with a different rendering technology, and then at some point you figure out performance isn't there. Like, it's just weird, right? In the sense that if I'm working with Unity as a developer, maybe I used to feel that graphics is figured out for me, but it felt like I would have stopped feeling that for a while. Again, I think I'm hoping things get better there. Dots is, from again looking at this from the outside, watching this from the outskirts, there's like really good ideas there, but also there's so much complexity essentially that's introduced into the system from having these diversions, and I think it was some of the decisions are, I think, unquestionably great. For example, I don't know how this works internally. I would probably distinguish Burst from Dots. Burst, I think, seems like just a super great idea, super solid investment into the C# for games sort of unique value proposition that Unity has. Nobody else has this. Like, if you use Godot, it now has C# support, but Unity's level of C# like integration, investment, and improving on top of this is just so much greater that to this day, like, it feels like optimal from this perspective. So anyway, but so my point is essentially, if you've been following Unity for a while, then to me it started feeling like something is not great like a few years ago now. But this year, obviously, the whole pricing situation have made people reconsider. But there's not like a great alternative. There's Unreal, but it's like a different. You would probably use Unreal for a different class of games. And then there's a bunch of open source stuff, which, there's like promising stars, but I don't know if I would actually build a game on this technology yet. And then you can make your own. But like, building an engine on your own these days is very hard. If your scope is very, very narrow, intentionally so, then you can do this, and you should. But I think the issue is the ceiling keeps rising in terms of um, the level of quality of tooling, the level of investment into the runtime systems, um, multi-platform story, like everything is getting harder and harder. Uh, it used to be, for example, one like sort of random thing, but Unreal shipped Nanite, and now people are like some third party engines are implementing similar technology. I think people are asking about this for open source stuff. Like Nanite is clearly a step forward, a large step forward in the story of rendering geometry. This means that if your goal is to like render the maximal amount, render scenes with the maximal amount of detail, etc., then your expectations changed a little bit. And if you're an artist, then this always has happened with internal engines where artists look at what's possible outside and what's possible in Unreal and things like this and ask for this all the time. But essentially, the cost of like improving your renderer, the costs grow, and I don't know if this will ever stop. Having said this, so like if your target is something like medium fidelity, let's call it games, on a constrained set of platforms, maybe it's still fine to make your own engine. I'm not sure, but yeah, my biggest advice is essentially ask why you're doing this, because I don't think you're gonna sell your engine to anyone. As in, like, if your goal of a company is to make an engine, it's probably a bad idea. If the goal of the company is to make a game, then why you're building an engine, kind of thing, right? So, like, there is space still for smaller, specialized technology that's written from scratch. It's just that unfortunately the costs are rising, and so you have to really, really define the problem very well, and look at this and say, okay, it's actually fine to invest in in our own technology here, because maybe the scope is small enough, or maybe it's unique enough that just every other answer is still bad. For example, if you have a somewhat unique take on how to model your worlds, an example comes to mind, which is Dreams on PlayStation. That's has a very unique render scene representation, and like everything else is unique about this. If your ideas about world modeling are closer, or I don't know, maybe you're like starting an engine today based on Gaussian splatting, where everything is a Gaussian splat. In this case, it's probably fine to make an engine, because every single problem that you have, or like 70% of the problems that you have, are not adequately solved anyway by anything established. And so regardless of the baseline that you take, you'll have to have a lot of work ahead of you to make it happen, in which case there's benefits that come with your own technology. But yeah, it's a difficult sort of set of choices right now, because neither established engine feels optimal, and also starting a new engine doesn't feel optimal either. So I'm not sure what you do. And the open source efforts are like not really production ready as far as I can tell, depending on your definition of production. Like one Steam game is probably fine. Like a truly like if you are thinking, oh hey, mobile consoles, desktop, then it's like weird and difficult. Yeah, I think AMD recently shipped like a special ray tracing profiler, but I'm not. I assume the issue with ray tracing, one issue with ray tracing is that I think RADV implementation is like has like nothing in common with for a lot of the other portions of the driver. You can look at the hardware that's targeting and say, well, there is like a reasonably narrow gap between what the driver is doing and what the hardware can do. oh sorry, between like the interface that the driver exposes essentially and what the hardware does underneath. And like sometimes the gap is large, sometimes the gap is small, but in ray tracing the gap is like huge, especially for AMD hardware, but also maybe for NVIDIA hardware as well. I don't know how NVIDIA hardware works with ray tracing, but my understanding is that in both cases the driver portion of the ray tracing is like large, but in AMD's case it's like even larger because the hardware is fundamentally not like that ray tracing capable. Um, I, I don't really know. I haven't looked super closely into this. I'm thinking, by the way, one of the things I'm thinking of doing, except this calm thing, which I'm gonna work on for a few weeks more, but I'm not sure how long. One of the things I was thinking of doing is doing ray tracing in Vulkan, just as a maybe as a stream series. I'm not sure. One thing I haven't, so I was talking about how like early this year I finally backfilled this thing where like okay, everybody is excited about ML, like there is so much there and I don't know much about it. So I feel like I still don't know a whole lot about it, but I know way more than I used to. Ray tracing is kind of similar for me right now. I used to be very skeptical on ray tracing. I'm still a little skeptical on ray tracing, but I think it's more and more clear that it's like a very, very important fundamental part of the real-time graphics in the future. Um, as in, when NVIDIA shipped their 2000 series GPUs, I thought they were basically, I mean, I wasn't sure how much staying power this has, but now it's in consoles, it's an AMD GPUs, it's an Intel GPUs, etc. So clearly this stuff is important. But yeah, and with Vulkan, especially on Linux, it would be interesting because technically all of this is in RAD drivers, so you can just go and like change this code, and that's fun. But yeah, the issue essentially then with building a tool is you have the RAD implementation and the AMD VLK implementation that are probably completely different. And there are some things that are structurally similar because they must be, because you're solving the same problem with the same constraints, but the size of the solution is so large that so much is like hand grown. Like I'm sure BVH formats are different for one. I'm sure the way how the work is dispatched is different. Like there's so many things that must be different between the two drivers. I would totally understand it if this was just a thing where the tools just don't support RAD. It's fine. But yeah. I didn't know that there's no single Wayland. For me, there's definitely a single Wayland, but it's definitely in the state of disrepair. Let's see. Yeah, so I think the state of Wayland is it works, sort of, but I don't know. I had some issues with NVIDIA. Ubuntu still defaults to X when using NVIDIA GPUs, and it defaults to Wayland when using AMD GPUs. Wayland has some issues under NVIDIA. One very basic thing that I heard maybe will get fixed at some point, but it's like this is an example where like a lot of the stuff about Linux is just fine now, but there's some things that are just weird. So there is this feature called Nightlight, which I started using on Windows a while back, and then I went back to Linux, and it's like, oh cool, I need Nightlight. Nightlight changes the screen output depending on the time of day to like remove the amount of blue light that it emits or something like this. I like it. It reduces eye strain. It feels like it's less. It means that I can like go read something on my computer like late at night and then not feel like I don't know, like can go to sleep and it's fine. So I like Nightlight. The problem with Nightlight is it's the essentially what should be kind of like a full screen post processing, like a color correction thing, right? I think the way it's implemented is by using by changing the gamma lookup table, sort of repurposing it for a different feature. and the NVIDIA drivers don't support this. Now, the implementation on X is probably using something else because on X it works fine. But this is like, it's not a niche feature. It's sort of a niche feature, but it's a feature that's a first-class feature in GNOME. Like you don't have to install custom extra stuff. You just take GNOME and just open settings, and there it is, the nightlight configuration thing. And it just doesn't work in Wayland on NVIDIA. So I understand why Ubuntu is not defaulting to Wayland when using NVIDIA. It's just crazy to me that like this is the stage where we are in right now. I also heard that X isn't really developed for years now, and like X maintainers went to develop Wayland. And so it's like this Unity thing I was talking about, right? Just in the windowing space, where now there's like two implementations, and there's the old one that kind of works, but is old and has problems. And there's the new one that's just not ready and not ready and not ready for years and years, and it's weird. On AMD, it's fine, although there's more issues around Wayland that are just also mind-boggling. So one thing, for example, is Chrome on Wayland renders text very poorly if you use DPI scale, which of course you do because, you know, obviously everybody at this point, not obviously, but many people at this point would have screens that are sort of with resolutions that are larger than they used to have, right? And like maybe everybody has really good eyesight. My eyesight is not as good as it used to be. It was never that good, and so I of course have to use DPI scale. I should say right now my terminal uses larger font that I'm usually using, but whatever. I had to change config for the stream to work. So you enable DPI scale on the system level, and then you launch Chrome, and your texts are blurry if you're using Wayland. So this is, for example, right now the configuration that I have, right? The AMD GPU for desktop. It's easy to fix. It's just a setting somewhere. But it's like broken by default in Chrome. How can something be broken by default in Chrome? I understand Linux isn't the most important platform for Chrome, but like still, it's just baffling. And then there was a bug in Chrome with Wayland. They shipped something. I'm struggling to remember. It was also DPI scale related, but they shipped something where like the window, something didn't work right. I don't remember. The window resizing didn't, whatever. There was some very fundamental problem where they landed the change. The change didn't work at all on Windows or on Wayland with fractional, with any DPI scaling. I think maybe fractional. I forget. And then they rolled it back eventually, but it actually made it into the official Chrome version, like the stable channel. Yeah, so it's still weird. It is bizarre, but on AMD it's much better than it is on NVIDIA, so that's nice. Have I had a look on WGPU? I haven't studied WGPU. WGPU is, or WebGPU, I should say. I think WGPU is like the name of the Rust implementation, maybe, of WebGPU, whatever. I haven't looked. I've looked at the API before it released. It felt pretty nice. I thought for a while, and I still do think that out of the three graphics APIs that are modern, Metal, Vulkan, and DX12, Metal, Apple is the one that got it right. Metal has enough of the low-level features to make for a much more efficient driver than OpenGL or DirectX 11, given the same amount of effort. I think with DX11 there was like a decade and a half or whatever of tuning by graphics vendors and like heroic tricks. So it's different comparison point, but anyways, it's low level enough to make a fairly efficient driver implementation possible. It's layered in the right way. The base implementation, the base API for Metal 1.0, if you were, is actually a good way to introduce people to graphics programming, and simultaneously a good way to program like GPUs on a basic level, like if you have no expectations about like super advanced feature sets. But then there's like Metal 2.0 or Metal whatever it is now. Essentially, there's extra features that they added after this. There's things like argument buffers. There's things like tile shaders, etc. And for every feature like this, it's an extra way for you to get into this more advanced GPU functionality, to reduce driver overhead. Like resource heaps is one of the other examples. And it's kind of a pay for what you use complexity, in the sense that it's making the API more difficult for you to use, but it is optional and you can gradually introduce this to people when teaching them, and also in code bases when you're writing code. So the reason why I say this is that web GPU design feels very, very, very heavily inspired by Metal, and so it looked very nice to use. Here's the problem with web GPU. It doesn't work on my system right now. I have Linux and Firefox. I have Linux. I have Chrome and Firefox on Linux. I think neither of them right now support web GPU by default. I tried to actually enable this in Chrome, and like it didn't work after enabling this. I just gave up. I didn't look too deeply, but yeah, it's a thing there where, I mean, it just technically released earlier this year, but like still not on Linux. The I'm sure it's going to be fixed in the future, right? I want to say in general, web standards, things that start with web, have been surprisingly good. WebGL, I guess, is not great. But WebAssembly, I think, is very, very nice. WebAssembly has a lot of really nice theoretical properties, and also it's a really, really good practical target for the web. It has maybe a couple of small issues here and there, but I think in general WebAssembly is really good. There's like WebAssembly is getting interesting, I will say. There is a bunch of extensions to WebAssembly. Some of them I think are very good and clean and additive. For example, WebAssembly SIMD is very nice. I helped make it, so I am biased, but it's like a thing you can use, you cannot use. It doesn't change fundamentally computation model, like it's great. There's things that are interesting and complicated. So there's WebAssembly GC that I'm not sure how I feel about this. There's also some stuff that's fragmentational. There's WebAssembly 64, for example, which is very nice as an idea, but I'm not sure. Basically, there's like, for all of the stuff, there's ecosystem implications that are always unclear to me. I'm not even sure if you can link WebAssembly modules across, for example, GC or not, 64 or not, probably not. Anyway, there's some issues there. But by and large, I think WebAssembly is a huge positive development outside of the web. There's people who use WebAssembly outside of the web to do sandboxing. There is it's a nice enough compilation target. It's not quite, I wouldn't advocate to like build a compiler that only targets WebAssembly and then just use WebAssembly backends to run it. Like that feels still crazy, but I think it's a really nice portable assembly in a sense. Like you could do worse than picking WebAssembly for a bunch of tasks. So similarly, WebGPU has been very nice to see because it feels like it's filling an important niche that has not been filled. The one thing that I don't like about WebGPU, and inside the web browser it's fine, but the thing I don't like about WebGPU and WebAssembly for that matter as well is I started the stream by talking about my new project, where the premise of the project is deep stacks are bad. Deep stacks of technology are bad. This is just a fundamentally, I think, true rule. It doesn't mean the best technological stack is the stack of depth 1. But I think it means to me, what it means to me, and people may disagree, and this is fine. I think a lot of the progress of technology is based on deep stacks these days, which is fine. But I think when making deep technological stacks, it is easy to add a layer. It is actually difficult to remove a layer after this. And there's a lot of hidden cost associated with adding layers that you don't realize until it's way too late. So now you look back and you're like, how did we get to the state where software is this weird? And I think layers is part of the answer. The reason I say this is the one thing that's unfortunate about WebGPU is that it's like an API that hides another API inside of it. And this is going to be the case forever. WebAssembly at least has a shorter. In WebAssembly, it hides the actual computer behind it. But this is the thing we already do with compilers, and this is the thing we already do with the LLVM, etc. And there is purity there that is very appreciated in some sense. There is some soft guarantees on determinism, I will call them this. WebAssembly is not perfectly deterministic, but it's like very close to being deterministic, which is nice. With WebGPU, I'm just thinking, okay, so there's a WebGPU, and then it's gonna run on top of a library that's gonna run on top of the graphics driver, and then that's your best case situation because your actual situation is probably there's a couple extra layers there. Inside the browser, it's also not ideal because the browsers are doing cross-process communication, and so there is like that element in your graphics API, which is also weird. So there's things. So essentially my main criticism about WebGPU would be, I think it's important that it exists. I think it solves. It tries to improve the solutions to the problems that we have. It's just I wish we didn't have to have one more layer for this. It's already bad. So Vulkan is nice and all. Vulkan doesn't work on Macs or iOS. Well, it does, right? There's a library, MoltenVK, that acts as a layer. It's a non-portable layer or portable. There's some weird terminology there that I forget, but basically there's like some issues. There's some sacrifices that you have to make. This didn't. The reason why this is the case is Apple company policy. It's not a fundamental truth about technology that the way to implement Vulkan must be through like a metal conversion layer. It's just Apple will not implement Vulkan driver. That is what it is. It sucks. It also means that if you run a WebGPU program, you really have to target metal, because if you target Vulkan, like you go through Vulkan metal layer on iOS and macOS. Anyway, it's all a little bit weird. The space of graphics APIs in general is a little bit weird. But I think WebGPU specifically, I basically have heard mostly nice things about. I haven't tried it myself, so I don't have first-hand experience. Is the market good for graphics people? Oh yeah, do you mean like the job market? The job market is really good for graphics people in the sense. So okay, on one hand, I feel like the number of custom engines is going down from what it feels like to me. I'm not sure if this is truly true. There's a couple ways to ask this question. One is, how many studios do you know that are really big studios with really big franchises that have stopped developing their custom engine and are now switching to Unreal? The number is growing. I don't know what it is. So off the top of my head, Final Fantasy, so there used to be, Square Enix had internal technology for a while. They had some fragmentation there. At some point they made, I think, an effort to consolidate. They shipped Final Fantasy, I forget what the number is, something, 13 maybe on it. I'm not sure what 14 is based on. 16 is Unreal. And 50, I think Final Fantasy, is it right? Final Fantasy 15 is their internal engine, and then Final Fantasy 7 Remake and Final Fantasy 16 is Unreal. Whatever, I might be misremembering specifics, but like there's a big studio there, right? Another example, so the CD Projekt Red studio had an internal engine. They used it for Witcher. They used it for Cyberpunk. They announced essentially that Cyberpunk was the last game with that engine, as far as I can tell, and the next Witcher will be on Unreal. And I'm guessing if there's ever like a Cyberpunk next or whatever, or if there is a new franchise at some point, I'm guessing it's going to be Unreal based. The other way you can tell is by looking at the top selling games and ask what fraction of them are Unity or Unreal. I did this on consoles for the last couple years, and I think the fraction of Unreal is growing. The fraction of Unreal is surprisingly small in the sense that if your mental model is, oh, everybody's using Unreal, that's wrong. But I think the essentially, yeah, the number of engines get like slower over time. So this is unfortunate because the best way to do the maximum amount of depth in the work that you are gonna ever do is gonna be at the company where the area of choice for you, the area of expertise, is super important for the company, and the company believes in owning it full stack. Meaning, you want to work on graphics, you could work in a studio that does graphics on top of Unreal, or you can go work at Epic, or you can go work for a studio that does the graphics or like whatever, their engine is not Unreal, it's a custom engine. The maximum possible amount of, like, in my opinion, interest and just like the best work that you can probably be doing is gonna be either at Epic or the company that has a custom engine that's not Unreal, not at the studio that happens to use Unreal. Having said this, can you do interesting work based on Unreal and graphics? Absolutely. There's also an issue where if you're going, there's studios that tend to underestimate the amount of domain-specific engineering that they have to do if they are using an established engine. It's like, oh, we are using Unreal, must mean we don't need graphics programmers. No, you do need graphics programmers. So I think in some sense it's unfortunate that the amount of custom engines seems to be like shrinking. On the other hand, the studios, Epic, for example, is getting bigger as a result, right? And so there's like growing teams of graphics experts there. But also, if you are an expert in graphics, if you are interested and passionate in graphics programming, I don't think there's really going to be a time where like your skills are not going to be interesting. So despite the fact that I wish there was more diversity in the engine space, I think the need for graphics programmers is ever strong. I think it's going to continue to be the case, unless we're all replaced by AI or whatever. But I don't know much. Well, I won't comment on anything that I know about Hyperion, and then obviously I don't work at Roblox anymore, so I won't even answer Roblox specific questions anymore. Do you think it's possible for a hobby kernel developer to implement support aka driver for a modern GPU in the ToyOS? This is a very interesting question. The question is interesting because I've occasionally idly pondered on doing something similar, but I've never been crazy enough to go do this. I think the answer is yes, but then the answer gets complicated. So there's two aspects that you are fighting as a GPU driver developer, as far as I can tell. I've never written GPU drivers myself. One aspect is that there can be a lack of documentation on a lot of stuff. So if you are targeting an NVIDIA GPU in your driver, then like, God help you, because a lot of the stuff is reverse engineered, and that stuff takes a lot of time to reverse engineer. And a lot of, like, if you run into problems, you will not know where these problems come from, you will not have anybody to talk to, etc. The second problem comes from the fact that the thing is just so complicated. Like the GPU is so complicated. In some ways it's simple, but in some ways it's not. There is aspects of the GPU that are insanely hard, even though they don't seem like they should be. But I'm not. I know nothing about the area, so maybe they actually should be. My understanding is that the display presentation, power management. There's one more thing I was thinking of, but I forgot. Let's just say display management, power management is like insanely difficult. As in, there's so much involved in doing this that trying to do this from scratch is like really hard. The issue with that is this is like the basics that you have to keep your GPU running. So this stuff is hard. Now, one thing though to keep in mind is that to this day there's a lot of drivers who are developed. Hobbyist is the let's assume you are somebody who has infinite amount of time and infinite passion for learning, and sort of frame it this way, right? Because like I don't know what hobbyist means. For example, if hobbyist means, oh, you have like a couple hours every week to spend on your operating system, then maybe there's so much work to do that you'll just not be able to do this, if that makes sense. But let's assume this, and let's assume further that hobbyist also means you don't get an in the company, as in you don't get secret access to like documentation or whatever. So like right from the open perspective, there is drivers written to this day by quote unquote hobbies from this perspective. They're like often employed by some company, but the company pays for their time. The company doesn't provide them like resources that they couldn't get otherwise. So people like this develop open source drivers, right? Couple examples. The I don't remember how Radv got started. I'm sure people from Radv talk to people from AMD in some capacity. Radv is an example of a driver, but Radv is an older driver. So there's a recent example which is NVK. So it's a new Vulkan driver for NVIDIA. It's written by an employee of Collabora, I think, and Collabora is just a company, as far as I can tell, that funds this type of work. They don't have like a contract with NVIDIA or whatever, right? Another example is that you can run Linux on Macs, on M1 Macs and M2 Macs and M3 Macs. The project is called Asahi. Asahi has a GL and Vulkan driver. Again, GL and Vulkan driver there is written by quote unquote hobbyists. Like I'm sort of repurposing the word again, but Apple didn't give them documentation and didn't pay them to do this work. And I assume Apple doesn't have engineers who kind of can answer questions about this. Apple is like super secretive. How do these projects work? It's a combination of information that's available publicly. This is often the case for AMD hardware. This is not the case for AMD or for NVIDIA or Apple. A healthy amount of reverse engineering, I would say. I don't know to what extent this is the case for NVK. The previous NVIDIA graphics driver Novo that can display to the screen these days. I don't think they have a Vulkan component. And also the Asahi driver that I mentioned. A lot of these are based on like a lot of reverse engineering. This means you get the driver for the OS, for another OS like Mac OS, right, where the driver works, and then you reverse engineer it by studying the disassembly. You reverse engineer it by finding the places where the command stream is generated, and then read this command stream and then find patterns and then decipher commands from it, etc., etc. There's some other ways. So people do this, right? So I don't think there's a reason that it's impossible to do in OS, but it's certainly a daunting amount of work. One thing that goes in favor of both projects that I mentioned, actually, both the Asahi and NVK, both the Asahi driver and the NVK driver, is so the way the GPU drivers are structured tends to be there's like a kernel driver that does some of these like display management stuff and like power logic and whatever, memory management. And then there's the user mode driver that has like everything else, and it's like an iceberg. Like, well, I guess in the iceberg you see the hidden or the smaller portion, but like the user mode driver is like very big and difficult, or very big and like complicated. But both of these projects are part of Mesa. Mesa has built a lot of the foundations for a graphics driver. Things like shader compiler toolchain, state management primitives, uh, some memory management, presumably helpers, whatever. So compiling shaders by itself, for example, is difficult, and it requires a bunch of effort to do this yourself. You can do this yourself, but Mesa makes it easier. But yeah, so like, is it possible? Yeah. Would I recommend it? I don't know. It is definitely going to be very hard. And you're going to have to descope, like, I don't know, maybe, for example, your life would be way easier if you say, okay, I'm only going to support AMD GPUs because AMD GPUs have the best amount of documentation available openly. And also AMD has multiple open source drivers on Linux. So if you're stuck and you can't figure something out, you can go read code, right? Doing this for something like Nvidia or for something like Apple is like really daunting because you have to do a lot of reverse engineering, and this is fundamentally sort of challenging, right? But yeah, like, would I recommend this? Probably no, but it is definitely interesting. um, oh, Python Foundation package, Unreal Engine 5.3. Not sure. I assume this is like scripting the editor or something like this. I don't think it has anything to do with runtime. Oh, what is Unreal Directive? This is not Unreal. This is some other company. So this is, yeah. So yeah. Um, so scripting the editor is a very different proposition. Yeah, like, I mean, it is not surprising to me that this is happening. In fact, this is a reflection of the fact that Unreal just doesn't have a scripting language right now, right? What are going to do, script the editor in C++. Verse doesn't exist in Unreal yet, so yeah. But Python is definitely the language that you use for automation. Could be build pipeline automation, could be like, I don't know, machine learning training automation, could be editor automation, large parts of Blender UI written in Python, etc. Like, Python is very obvious choice for this, so I'm not surprised. This is fine. In fact, in my project, I said it's in C. I technically lied, because there is some number, there's like 200 lines of Python, and it's kind of important 200 lines. I could get rid of them. It's actually fairly easy now to get rid of them. I've written like enough C code that I can just delete the 200 lines of Python code, but I would have to replace them with, like, I don't know, 500 lines of C. I'm actually considering this because there is like a problem that I'm gonna need to solve soon. I'm hoping to be able to solve this in PyTorch, and hopefully it's gonna be fine. Python is like bad to process a lot of data. It's a bad language to process a lot of data, right? Because like, it's not very fast. The reason why it can be fast is if you have libraries that are written in C that do essentially array-based processing. So it's the thing that I was talking about earlier in the stream, where in Python it's like, oh, multiply two objects together. And actually there's like a C implementation underneath that says, oh, both objects are like gigabytes of data. We can we can solve this problem. It's okay. I'm working, or so like, as I work on these smaller bit representations of weights, I'm thinking of things that, as far as I can tell, people haven't tried before in this field. I don't think these are outstanding ideas, as in, I'm not like, I doubt that doing these will improve the state of the art in some way, right? But for the thing that I'm doing, I feel like it might be enough of an incremental benefit that's interesting to me. So I kind of want to try them out. The problem is that they involve essentially doing custom compression of these weights. Think of it as block compressed textures where there's like a few bytes that represent a few different pixels and they have interesting bitwise encoding schemes inside it, and GPU natively supports decompressing and stuff like this. If you were to write a texture compressor to block compressed formats, you would like not want to use Python. And if I gave you these array libraries for Python, you still might not want to use Python because it's difficult to reformulate your code in a way that actually maps to these giant array operations, even if you end up having to compress like a lot of pixels. So, and you do this one time when pre-processing the data, except that for me, one time is like 10 times a day as I'm like experimenting with stuff, trying out new models and whatever. And B, you end up processing like gigabytes of data every time. So this model that I'm working with most right now is like 15 gigabytes source. So like it takes time to process 15 gigabytes of data. And if you use Python, it takes like a lot of them. So I'm thinking about maybe, and I really don't want to do the Python extension thing because I think it gets me back into this stacked PyTorch thing where I have to deeply care about the interaction between layers and whatnot. So anyway, maybe I'll rewrite some of this to C, maybe not. Maybe this whole project is rewrite everything to C. We will see. I am thinking about this. All right, yeah, that was a question. What do I think about Jai and Jonathan Blow? Jai is a little bit interesting. Here's a couple things I'll say about Jai. So one is I think early Jai had a lot of fun ideas that I feel like just weren't super explored. And I think that's super interesting to see. I've watched all of the early Jai videos, not the videos where Jonathan works on the compiler itself, but like the ones before this where he talks about the language design and stuff like this. And they definitely get you thinking. So I think that's like super nice. The way Jai syntactically attacks the problem has felt very appealing to me. It's a small thing. Syntax is like not the most important thing in language by far, but I looked at some other languages. So for example, Zig feels like a really nice language. There's something about Zig syntax that just doesn't jive with me, and this was the main reason why I kept putting back. So there's two C++ replacement languages that are popular these days, Rust and Zig. Rust, I think, is obviously like an established programming language at this point. Lots of people write production software in it. It's stable. It has tons of people improving it, etc. I don't really write code in Rust. There's some reasons for this. I occasionally, I don't know, like if I need to write code in Rust, I will. In fact, when I was starting this project, I was thinking about Rust as a language because it would cover one more niche with this project that I felt was missing, which is recent Rust experience. I wrote Rust for a few months, like years ago, and then stopped. The thing that stopped me was that I realized I would have to write a lot of CUDA. Rust CUDA story is very weak right now. And when you're writing CUDA, you're writing C++. So, like, what's the point? It also feels very nice to have to solve every problem by hand. You can impose a restriction on yourself when using Rust, but Rust has so many libraries that a lot of the problems are used, it feels like, to like, I don't know. Well, so again, JSON parser is not the best example. Here's a recent, very basic example from like yesterday. There's this tokenization process where you take the text and you break it into tokens. it's for people who have never worked with ML language models. They might not be aware that this thing exists. Let me run this on the CPU so it doesn't take out my system. Right. So like you give it this phrase, what is the meaning of life, with a question and colon and like question mark and stuff. And it breaks it into these however many tokens this is. This is like a special token that's like beginning of the sentence. It feels a little redundant, but whatever. And then it adds, you need to add a space, don't ask me why. And then some things are just one character, and then some things are words. And then, okay, this is actually a bad example because it's either a character or a word, but I don't know. Let's see. So if you tokenize the word verbosely, it's not one token, it's like three. I think the usual rule of thumb is like 3-4 characters per token if you're using English. If you're using like so for people who are not Russian speakers, this is Russian. This model, surprisingly, let me actually. I don't really use Russian a lot, so I didn't anticipate this, but this model surprisingly forget I said anything. I never actually tried this specific one. This is garbage. I thought I tried this. I didn't try this specific query ever. Interesting. So maybe I broke something recently. Maybe this never worked in the first place. But the point is, different languages like tokenize differently and stuff like this. The thing you need to implement a tokenizer, or one of the tokenization methods, is a priority queue. So I wrote a priority queue yesterday with like a heap. And you need a heap, you need to hand code this because C doesn't have it built in. So like I wrote the heap implementation and I'm like, I almost never use priority queues. I use things like hash tables and arrays and sorts all the time. So I know I can implement like 5 different versions of each. I know what's the best one for every given purpose, etc. I never asked this question about priority queues. In general, heaps are not my favorite like data structures. So I think I never used the heap. I used heap as like a heap sort implementation, and it's only ever in context of like a fallback that you never take. Anyway, so now I am thinking, is there like a better way to do this? If I used something, any language where, if I use C++ where there's a priority heap in the standard, I would like have written this code and forgot about this. But so staying low level, extremely low level, forces me to ask interesting questions about some fundamentals that are valuable to ask. Having said this, of course, it would be fewer lines, it would be nicer in some ways in Rust. But yeah, so like if not for CUDA dependency, I probably would have actually written this in Rust because I thought about doing this in Rust. And then I realized I don't really want to explore the CUDA in Rust subject. So, and the reason why, right, sorry. So going back, so the second language that's popular in the space is Zig. And somehow I'm not a huge fan of Rust syntax, but I'm okay with Rust syntax. Something about some parts of Zig syntax just make it's stupid sort of, but like it doesn't jive with me enough to just make me want to pick it up. Jai, something about the syntax makes me want to pick it up. Unfortunately, Jai doesn't exist. Well, it's like an inside joke, but Jai does exist, but you can't use it, right? It's in closed beta, has been in closed beta for a while. People have written code with it, etc. Unfortunately, I can't like right now go download a Jai binary and start writing code in it. The other issue with Jai, this is not a problem for this project, but for this project again, because of CUDA, like I don't know what else I would have used. Um, a problem with every language that I have that is not C or C++ is that eventually, so a lot of the work that I do, it happens to be work on libraries. I haven't really talked, for example, about Mesh Optimizer at all on the stream, but I still am working a little bit on Mesh Optimizer, and I expect to work a lot more on Mesh Optimizer next year. But that's a big part of this is a library that other people integrate, and if this is not written in C, then it's more difficult for people to integrate with it. So it's like I would there's people who want the whole world to be written in Rust, but that's a separate story. And then, but Rust at least is like definitely, it definitely is a reasonable choice at this point, I think, to invest into this ecosystem. This ecosystem will stay for years and years and years, etc. Jai is not obviously, it doesn't obviously have staying power, right? Especially given the fact that it still doesn't fully exist. So definitely when Jai actually fully comes out in public, I will try this because the language, from what I've seen of the language, it felt nice to write code in. And also the one big thing that Jai has that Zig also has, to some extent, but not as strongly, but Rust doesn't, is the focus on iteration time, focus on compilation speed and stuff like this, and also focus on practicality. Um, to this day, the biggest thing that I'm thinking of when I think about Rust is, oh man, compiling is not very fast. And Jai, it's one of the points that Jonathan, I think, focuses a lot on. Anyway, so yeah, I'm interested in Jai. I don't know to what extent it has staying power, but I definitely would try it out. There's now the language that has similar syntactic structure and some similar kind of qualities of implementation, but some qualities are not shared with Jai, so I haven't really tried it. Is Odin. I think Odin was inspired by Jai. In general, the really good thing about Jai is I think it inspired a lot of language development in this like low level space, which is cool. As for Jonathan Blow as a person, I don't know. I don't know him. Some of his takes feel really wild to me. Some of his takes feel alright. I feel like, yeah. So I don't really know what to say here. But I don't know him, so a lot of the stuff doesn't translate well. Oh yeah, somebody mentioned Odin. Oh Mojo. Yeah, Mojo. So, use case for Jai problems to trying to solve. Yeah, basically here's the deal. So I started this project in C. Okay, so this has CUDA in it. But if I were to start a new project in general today, what language do I use? This is not an obvious question. So I could use C++. C++ is like, I have zero hopes for C++ at this point. Specifically, C++ just feels like it's moving in a direction that is orthogonal from the direction that I would be interested in. And a lot of the fundamental problems with it either remain or are being solved in a way that just makes me like, I don't know, question my commitment to C++. So I don't really like C++, but I am extremely productive in C++. This is language I've used for, I don't know, 20 years now. It's been a while. I don't have a lot of C++ scales poorly from the quality of code perspective. As in, like, if you are writing a giant project in C++, there are so many issues that I predict you will have, and you have to fight them so hard from the beginning, and it's hard. And you integrate like a third-party library, and it will not abide by the rules that you've set for yourself. So like, it's bad. But I don't personally have the problem that I think a lot of people will come to you and tell you, oh, like you should use Rust or whatever, because you're just gonna spend so much less time like debugging code because you're not gonna have these memory errors and stuff. I don't have this problem with C++. I do have the problem with C++ in that I'm not perfect. Like I'm writing the same C++ code as like other people are, and it's gonna have bugs and mistakes, and some of them are gonna like crash your program or result in an exploit or whatever. But I feel like it doesn't impact my speed hugely. The fact that these things exist. Having said this, I recently talked to a person. We were chatting about other stuff, but we were talking to Rust about Rust. He said something interesting. He said he used to use C++ like for years and years and years, and then switched to Rust. And the comment he made that I don't know how to evaluate because the only way you evaluate it is by trying to use Rust for a while. And again, I don't have a project to use it in for now. Is that it's surprising how much cognitive overhead there is when using C++ that has to do with these like memory tracking and out of bounds checking and God knows like what else. And the reason I'm mentioning, people bring this up before, but people bring this up when talking about Rust, but the way I heard this argument before usually goes like this. Look at all of these problems that you have to spend a lot of time on when writing C++ code. Rust doesn't have them. That's not the experience that I have with C++. There's an argument for Rust that I totally buy, which is look at all of these subtle bugs in the code that you have shipped, which are going to be exploitable. Like I'm not claiming I can write some unreasonably exceptional C++ code. But the thing essentially that this person said was maybe you don't know that you're spending cognitive effort on this part of the language because you've been doing this for so long, it feels like it's coming for granted. And what it made me think about is, well, maybe it is a thing I'm just spending mental energy on, and maybe if you remove this thing, I would be faster, even though I don't recognize this as a huge part of what's going on in my day-to-day, right? However, there's a flip side to this. In Rust, every operation on indexes is bounce checked. And to me, it feels like people, by default, and to me, it feels like people go to unreasonable defaults, converting their code to the style that I consider to be worse, with like iterators and whatnot, as like a default. And a lot of the times when they do this as a reaction to, oh, I wrote the code is slow, let me look at what's going on, oh, there's a bunch of bounce checks, let me fix this by rewriting my code. I don't want to do this, and so I'm not sure if one balances out or not, whatever. Anyway, so there's reasons to pick Rust, there's reasons not to pick Rust. The and then what else is there? So there is Zig. Zig has promise. Zig is still not stable. This means code that you write in Zig will break occasionally. Zig still is in super active phase of development where there's some things that work, some things that don't work. They're like in the middle of the compiler switch right now. Like it's great, but do I want to kind of bank on this being the thing? I don't know. Everything else though is like not even there. So Odin, somebody mentioned Odin. I also touched up on Odin, right? There's actually a company that's doing production software in Odin, which is great. So like Odin is a language that exists that you can use. But again, from the standpoint of do I want to invest in an ecosystem? Is there an ecosystem of code around Odin that is very large? You can't compare with C++, but like Rust large, right? Not that I can tell. So like, do I want to invest a whole lot of my time into this? I'm not sure. So Zig maybe, I'm not sure. But again, Zig has none of the languages for some reason that are not C++ obviously work for me, so it's kind of weird. This brings me back to Jai, right? Imagine you're in this position where you're starting a new thing. C++ just is depressing for many reasons. The language doesn't go the way you want it to go. There's giant tooling problems that are not being solved adequately. The whole thing is hard, and also the language has a complex, diverse culture of writing code in it that more and more gravitates towards the culture that you're not comfortable with. For example, memory allocations everywhere, stuff like this. It's not. I'm not describing C++ super fairly right now. So if you love C++, don't be offended. I'm painting a point of view of a person who does these things, which I think is Jonathan Blow. And then you can agree or disagree, but like it's not my opinion, but it's also not my opinion. It's a little bit different. I think about these things a little bit different. So you have this. Then you have Rust, which when Jonathan started Jai was just not even like that interesting as it is now. But also Jai, not sorry, Rust. Not everybody would agree Rust is solving the problems that they care about. For example, for again Jonathan Blow and for me as well, the biggest issue with C++ by far that I have is not the lack of like modern features or whatever. It's just the um, scaling properties of compilation speed and stuff like this in large systems. Combined with maybe one second thing I would offer that I really don't like about C++ is how there's still so much simultaneously there's so many fundamental things about computers that have been there for a while that C++ just isn't solving very well yet. So for example, CMD is something that C++ is solving very, very, very poorly right now. And the end inside is apparently std_cmd, which every new every new standard library development in C++ is depressing for other reasons. But I don't have an opinion on std_cmd. I haven't seen. But like, so you look at this, you're like, okay, I have a lot of problems, right? And my problems, there is this Rust thing, which seems to like is getting traction, but it's focused on problems that I don't feel like I have. What do I do? Well, you write a new programming language. So this is why, right? There is nothing else that exists that feels like it's aligned with how you see the world. You go and create, which is great. I think Zig for me is more aligned, especially if you look at this lens through like the lens of game development or whatever. Where if you're doing client-side game development, exploits, memory safety are not like as big of a concern. If you're doing backends, then I would probably go Rust these days, because like I'm not sure what else would you do. Probably Python is too slow, JavaScript is too slow, and like nobody, I don't know, Node doesn't seem to scale super well. So like Go, I guess. So if you like garbage collection, you Go. But Go is a less nice language. Otherwise, you go Rust. So for backend, it feels reasonably straightforward. But for like games, for example, it's not. So this is why Jai got created, and I think it's a very legitimate reason to exist. This is part of why I'm hopeful for Zig, because maybe Zig will be this language where it's it's somewhere in between Rust and C in a sense, right? It doesn't really give you the same static guarantees that Rust has, but it has some of them available through other means. And a big reason why people like Rust isn't the borrow checker part. It's basic, simple things. If I were to add a unit test to a Rust project, I could go in, add a function, mark it with a test attribute, and then that's it. My test is done. It solves so many problems that C++ has, and C++ you start by, let me like find an appropriate unit testing framework, and there's different ones, and they're all different, and then it's just, anyway. So, and this is to say nothing about things like built-in enum types or like sum types and stuff like this. So anyway, I'm hopeful for Zig because I think Zig has more of a chance of having a staying power. But Jai was created when Zig I think didn't exist. So anyway, um, I don't think this take on Rust compile time handling is fair. I think the take that is fair is this is a hard problem. Rust has done a lot of super interesting work on compile times, but uh, Rust's approach to compile times is kind of like if it's difficult to explain, but it's like the so John Blow, I think, touched on this when he started Jai in one of the early videos. I don't remember. Here was his take, which I agree with. Computers are insanely fast in terms of peak compute power today, and we don't know how fast they are. And this is kind of why not. This is one of the issues that I'm scratching with this project, with the comp thing. Even though where I'm saying I'm not going to use the GPU's full capacity because my problem doesn't allow this, but whatever. So you have a computer. So you have my computer. My computer is a good computer, but it's not a crazy server build or whatever. It's like a CPU that I bought. The CPU was a little bit expensive. I forget, $600. You can get a cheaper one. But so I have this is an interesting whatever. So it's a 16 core CPU, but you have two-way like simultaneous multi-threading, hyper-threading, whatever you want to call it. So it's like between 16 and 32 threads. Let's say it's 16. It's somewhere in the middle. The numbers that you usually hear are 30% from multi-threading. So whatever it is, like 24 cores worth of compute. And then like every core can do CMD processing, and then for some widths maybe it's not gonna do this very well, but whatever. You multiply all of these things together and you get so much raw compute that it's kind of scary. And then you ask, here's realistically, I don't know, like 10 megabyte source code base. 10 megabytes is not the size that you get to when you work on like large engines and large code bases. You get into like a gigabyte. If you go to Google, you get into like, I don't know, want to know, but whatever, like let's say tens to hundreds of megabytes of source code. It feels like a scarily large number, and yet actually it's not that large if you compare it to these like insane numbers that you get out of the CPU in theory. The problem is bridging the theory in practice. The problem is, for example, you go compile like a Rust program. Let's say my Rust program is a single crate, and it has however many lines of code. A very, very, very large portion of this compilation process is single-threaded. So suddenly it doesn't actually matter anymore that I have 16 cores plus hyper-threading. It's as if I had one core. Rust does parallelize a little bit within a single crate, but only at the LLVM stage, and I forget what the default settings are, and there's other problems. But so like everybody is aware that these problems exist. I'm not trying to explain like super new things. I'm just saying. And then you look at what this one core is doing. And turns out like a crazy amount of time there is spent on like branch mispredictions or cache misses, which is like another 100x cut or whatever to the CPU compute. So suddenly you're taking a problem that in theory CPUs have a lot of power for, and solving this in a way that CPUs actually don't have a lot of power for, and actually everything is very slow. So this stuff is a problem. And there's two ways how you can attack this problem. One way you can attack this problem is to say, actually, between runs, you're gonna speed up your code in the usual ways, but one fundamental question is, are you gonna do the incremental compilation or not? And the Rust's answer essentially, I think, is we have to. There's no world in which Rust is going to be fast enough without incremental compiles. And so for incremental compiles, they're doing a lot of really, really interesting work, because incremental compilations are difficult to make correct, and Rust has a really, really big focus on correctness. This is appreciated. So they're doing this work to essentially decompose your compilation process into a series of questions. And every question is like a functional programming style question, as in it's an execution of a function that has inputs and an output, and it has to be pure. There is no global state. And then you cache these queries. This means if you ask again, you can get the result from cache. So in theory, this is super nice. There's a lot of practical problems with it. But the Jai answer to this problem is we are going to brute force this. As in, we are gonna maximize the, well, the theoretical answer, the theoretical GI answer, I don't think there's there yet at all yet. But the theoretical answer is this: we're going to maximize the utilization of the hardware that we are going to use to compile our source code. And in principle, our hardware should be fast enough to just compile the code. Like it should be. And when it's not, it doesn't mean the problem is fundamentally infeasible to solve. It just means we have to change how we approach this problem or the definition of the problem. Now, will Jai fully get there? I don't know, but I think this is a problem statement and approach that I can emphasize with. Let me give you a very basic example that will illustrate this. This is not from Jai. I think this is from, it's not even from Odin, but I've been told that like this is an approach that some people are taking to speeding up Odin compilation, which I thought was emblematic of the thing I'm talking about. So let's say you have a program, it's a large program, and then you are compiling, it's a large file and you're compiling this one file. And it has a bunch of functions, foo1, foo2, etc. And then they call each other, and it's a statically typed language, so they have types and stuff like this. You can ask what happens when we compile this source file to machine code. Usually there is a sequence of transformations that happen, a sequence of steps. So you have to parse it. Parsing feels like it should be hard and slow, but in practice, parsing can be reasonably fast. There's parsers that aren't fast, but if you're not parsing at like I don't know. Like your code should be parsing basically at 100 megabytes a second, ideally more, but at least 100 on one core. And if you're not, you have problems in your parser that are fixable, or you have problems in your language grammar that might not be fixable because maybe your language grammar is static, but this is part of the design of the language. You have to take these things into account. So parsing is not, and 100 megabytes a second means that if you have a 100 megabyte code base, then it takes you a second to parse it, which still feels like it's a lot for an incremental build. But then in practice, this is also trivially parallelizable because you parallelize by file and you do this first, like up front, for example. And so 100 megabytes on 16 cores should take you like 50 milliseconds or whatever to parse. Now, maybe it's more, maybe it's less, I don't care. The point is, I think people, and sorry, the other thing is parsing is linear. It has to be. If it's not linear, you have like problems somewhere in the grammar or whatever. Once parsing is linear, this means the cost isn't just small, it's also predictable. I add 50 more megabytes of code, it takes me like, I don't know, whatever, a few extra milliseconds on multiple cores to parse. The thing that happens after parse gets less predictable in terms of runtime, and also worse. I'd say in general, if parser is like your slowest part of the compile, like you've won the game. Because now then you like rewrite your parser and it's good. And by the way, this is not getting into, people parse JSON at like gigabytes a second these days by using CFD and stuff like this. PugXML parses XML at like 600 megabytes, a gigabyte per second, I forget, it depends on the file, without doing a lot of crazy XML CMD stuff that people are doing. So like, it depends on the effort that you willing to put in, and depends on the grammar and stuff, but like you should be able to get the parser to be very fast. What happens after parse though is difficult because then you get into more expensive processing that's harder to parallelize in a sense. So let's go back to this one file. So you have a bunch of functions there, and then you run different compilers talk about this differently, but can say there's a semantic analysis phase, can say there's a type checking phase. Sometimes they're one and the same, sometimes they're different. Something is okay. The problem with these guys is that they are getting more difficult to parallelize. So for example, to do type checking or semantic analysis or whatever on a function, you have to know the types of all of the other functions, and usually it's like sequential in the file, or sometimes there is circular references, which is even worse. And then your module depends on other module, and so you have to type check that module um, to actually be able to type check your module. And then when you're type checking an individual function, you have nonlinear algorithms. Luau has this big problem in its type checker that I think is probably not solvable. There was no way around this because this is not a language that's designed from scratch, if that makes sense, right? If I designed the language from scratch, I think I would end up with very, very different things. But in Luau, the issue is the type checking of every function can be like exponential in the size of the function in terms of runtime, and it's like something that's hard to control for. But you're solving problems end to end, you're designing a language and writing implementation for this language, and you're taking all of these things into consideration when you're doing this from day one, which is a luxury that Luau didn't have, right? So then here's one thing that you can do, and I'm not suggesting you have to do this, but I'm bringing this as a thing to think about because this is the type of choice that you can make in languages like this, and maybe you should. So let's say that the functions, so there is foo1, foo2, etc., foo3, etc. Let's say that we have a constraint on these functions, which is that the arguments, the whole signature of the function has to be statically annotated at its declaration. So you can't say, oh, foo1 has a type. You can say, for example, foo1 accepts A, and the way we discover the type of this A is by type checking the body of this function, or the return type or whatever, which C++ already violates this constraint, by the way. C++ didn't used to violate this constraint, but they have auto return types in C++, I think at 17 or whatever, that violate this. Like you have to type check, for some functions, you have to type check the body of the function to like actually know the arguments. Luau doesn't conform to this constraint, of course, Luau type checker. I forget about Rust. I think Rust doesn't follow this constraint either, but I'm not sure. But let's say you have this constraint and you impose this constraint. So like if foo1 was generic over A, you had to explicitly say so. If the argument of A was a number, you had to declare that this was a number on foo1. And this has to be the case for every single function that you declare, let's say at top level. Is it a reasonable constraint? I would actually argue maybe yes. There's other benefits from having this constraint. Your code becomes less fragile this way because you rely less on type inference on the interface, so on the top level declaration. If you export the function, you probably want this requirement anyway from your module because it's really, really dangerous to be exporting type inferred function signatures because, you know, changing the implementation of the code now can break compatibility, which is bad. So let's say you had this constraint. Here's what you can do. After you have parsed, and we are assuming parsing is linear, there's other ways to parallelize parsing that may be very practical. But let's say it's not a problem because there are so many source files that is parallel anyway, but the source files that have dependencies on themselves, and so it's hard to type check in parallel. So then you say, well, okay, if every function signature is explicit, then you can split your type checking or your semantic analysis or whatever you want to call it into sort of two parts. The first one is maybe linear within the file that sort of resolves the names within the signatures. You might have to do this, for example, you might have a type T equals number, sorry, this is not visible, type T equals number, and then you have foo AT, right? So you have these two different top level statements. You can't tell what T is without like evaluating sort of, right, the first one. So this has to happen. But you don't have to look at the body of foo1 to determine this. So split it into two parts. The first part only looks at top level, and it only does this name resolution kind of phase, right? You don't even have to do actual type checking, as in maybe there's some conflicting stuff here. Maybe like, I'm not sure what it would be. if you have decal type and like certain language features make this harder, the answer is you basically don't add these language features. Anyway, so once you do this, you do the first pass that's linear through the file, where you just establish the types for every function, and this should be very quick because you're just doing name resolutions, and a lot of the stuff might be pre-resolved by your parser. Luau parser, for example, pre-resolves identifiers as part of the parsing process, which makes the parsing process like a couple percent slower, but makes every single stage after this like faster, so it's good. And then suddenly the results of the type checking of individual functions do not depend on each other. Even if they call them recursively, like it doesn't matter. Which means you can parallelize it. Which means that even if you changed one file that happens to be like 500 lines long, compiling this one file will be faster on a 16-core processor because we are gonna multi-thread the semantic analysis. There's other things that you have to do. One other example, this is something that LLVM struggles a lot with, is to the extent that you're relying on allocations from the global memory allocator in your implementation, your thread safety performance will be impacted. Your threaded type checking performance will be impacted because you're going to hit scaling issues on the system from the memory allocation perspective. The answer is like you don't do this. So there's other things that you have to do, but like this is an example of an approach that you don't have when you're taking existing language probably. But if you're designing a new language and you really care about compilation performance and you really care about machine efficiency during compilation, this is one of the paths that you probably honestly take because it's so good for you and for your users. Your users will thank you in the end. Some of them will complain about the lack of type inference functionality in your language, but it's fine. Anyway, right, sorry, Mojo. Yeah, sorry about... I should have picked a different... I don't know if we can fix it at this point. There's nothing super interesting written here. There's a width. Yeah, that's usually too small. Let's set. Whoa, it's still very small. Interesting. Oh, wait. Whoa. My whiteboarding thing. Okay, no, it's finally picked it up. For some reason, this is the thickest it can go. I don't know why. Anyway, it's not. I hope like even the verbal explanation here was enough. Point is, so getting back all the way, this is, I think, this unique opportunity that you only can get when you're simultaneously designing the language and writing a really, really, really ambitious implementation of the language, right? And to the extent that Java languages like this take these opportunities, I think that makes me excited about them because A, it's new ground, which is fun in the implementations of the programming languages. B, it's actually better for users in the end. So that's super cool. So like one other example in which Rust attacked this problem. Somehow they didn't. I was hoping for more things. I'm not quite sure. I haven't looked into this in detail, but essentially one problem that all of the languages like this have is you always run into LLVM compilation performance. Let me unpack this. LLVM is an excellent compiler if your goal is maximum efficiency of the resulting code, which is fine. It's gonna be a little bit difficult to beat LLVM at code generation quality. I think you can do it on a constraint problem. If you're doing like a vectorized compiler, for example, vectorization on the compiler, like ISPC or something like this, then I think you don't have to use LLVM, depending on how you design your language again. But in general, it's very, very hard to compete with LLVM on the quality of the output code. However, it is very easy to compete with LLVM on the performance that it takes to produce that code. And this is really important when iterating. So C++ has insane problems even when building like any kind of binaries. But for a lot of languages like this, it might be practical to use LLVM for like actually generating the output binary. It might be fine. Maybe it'll take time on your CI build, but like maybe it's not that much time. But one big issue that every language like this hits is when you're working on the code. So let's say your optimizations are disabled or very light optimizations only are enabled. Your compiler is still very slow, and your language is spending a lot of time, your language compiler is spending a lot of time in LLVM's code generation. If you're using LLVM and you're not bottlenecked by LLVM's code generation, then I claim you have a lot of work, just like a ton of work to do on this first part that comes before LLVM. As in, like, your expectation when building these native languages should be that you're bottlenecked by LLVM to like an insane amount. I don't know. You should be spending like 90% or whatever if you're using LLVM in LLVM, I would expect, even in debug builds. Now, it's not to say that you should leave it there, but this would be my expectation. Now, let's say you are there, then you have to like write a new code gen that doesn't use LLVM. You can beat LLVM by like very large amounts on the code compilation throughput by sacrificing output code, by sacrificing some other things, but like the delta there is not funny. I was surprised because I was hoping that Rust compiler would be way faster through the crane lift effort, but it didn't quite happen. And I haven't analyzed this in detail. I think one problem in Rust is it's not 90% LLVM. Like the stuff before LLVM takes like very, very appreciable amount of time. But the second problem I'm less sure about. Maybe crane lift isn't as fast as you can possibly do. I'm not sure why, but I had hopes. Anyway, Mojo, we are. Wait, did we start 10:30? Oh wow, we are 3 hours in. Okay, we are probably getting close to the end because I didn't have a super hard cutoff for this, but I didn't expect this to be 3 hours. Anyway, so let me talk about Mojo because people asked. Yeah, I'm not super sure about Mojo. It's the thing where I really like the problem that it's trying to solve is very real. I like some parts maybe of the solution, but I think on the whole I don't know. I don't love this. It's somewhat practical. So let me back up. So I was doing this ML stuff earlier this year with Python. All of this is like Python, PyTorch, etc. You run into Python performance limitations like a crazy amount. You run into PyTorch limitations in terms of performance as well. I already talked about this, but you also run into Python performance, and it's it's like a big problem. It manifests in many ways, some of which you may expect, some of which you don't. One thing that I talked about, for example, is the GPU efficiency, where you have A times B plus C, and then the cost of this operation is like bandwidth bound at every stage because it takes A times B, saves the result to memory, loads it back from memory, does plus C, etc. It's all bad. Even if the sizes there are small, you still run into a lot of problems just because of the Python dispatch overhead. Python plus the PyTorch plus whatever layers, like there's a deep stack. The other thing that you run into a lot is the raw performance that you get out of the Python code that you end up having to write. So you use all of these libraries that are written in C and it's all great, but then like you need to do something fairly basic. I had this moment where I needed to tokenize some code and I wanted to write a custom tokenizer for like some reason. And I wrote it in Python and it worked. And it was so slow that the network was not billions of parameters, but the network was like, I forget, hundreds of millions of parameters. And like the cost of training was super bottlenecked in the Python process, like insanely bottlenecked. I have some other examples like this. Then so like it's a big problem. The fact that the language is slow. And by the way, for people who have the mental model of like an interpreted language or whatever, or that when they think about Python, like you're not close. As in JavaScript or Luau interpreters beat Python interpreters by like a lot. I don't know what the numbers are because last time I looked was a while ago. It depends on the code, etc., etc., etc. But it's easy to get into a situation where you could have rewritten the code in Python in like JavaScript interpreter and gotten like, I don't know, 100x speed up, and then like you enable the JIT and whatever. Python has a JIT as well, but it's not. It's very, very separate from the language. A lot of people don't use it, I think. Anyway, so the fact that the language has performance issues is a real problem. Here's the even worse problem. So you're using all of the C libraries, things are great. Remember, your computer has multiple cores, more than one, even more than two. When you take these 2 GB size matrices and multiply them together, PyTorch, even if you do it on CPU, PyTorch will actually use internally threaded, I think it's OpenMP based, but maybe custom scheduler, I'm not sure, custom thread pool, I'm not sure. Implementation, so like you are using multiple cores if you have a single, so that's fine. But there are cases where you use a C library that doesn't do this, or you use a C library that happens to not have this optimization. One example is I worked for maybe a month or so with images, and it's like, oh, I want to read an image from disk. Well, it's in JPEG or PNG or whatever. These decoders are not that fast. They're not that slow, but you're using one thread to decode one image. So like there's a problem there. Okay, can you use multiple threads in Python? Well, the answer is both yes and no. You can use multiple threads. Python code will be serialized because of the global interpreter lock. C code, in theory, will still be able to run parallel. In practice, you get dramatic efficiency losses if you have these like a bunch of C code that you're running, but sometimes there's a GIL, sometimes there isn't. You do like 16 cores and you're getting like 2x throughput or whatever because of the constant synchronization and constant going back to the Python interpreter that grabs the lock and stuff like this. Like it's not actually great. You can work around these problems by using multiprocessing, which spawns a new process with a Python interpreter, and then communicate data with pipes and stuff. And PyTorch has code that will help you do this for data loading specifically, which is fine for basic stuff. It's really then you run into further issues where some packages are not like friendly to this style. I had some crazy problem where like I forget, there's some incompatibility between PyTorch and processing and CUDA, so you have to. It's all sad. It would be much nicer if you could just spawn a bunch of threads and they will just work without syncs. Python is working on having an option to remove the global interpreter lock. I am hoping this will work well. But in absence of that, and in presence of other options, and taking into account the whole stack problem that we started this whole 3-hour discussion with, where you have like PyTorch, and then it's on top of C++, and then it's on top of CUDA. And one issue with this layering isn't just that the code is split into these layers. It's the fact that these layers are written in different languages. You have to spend a lot of effort communicating data between these layers efficiently, stuff like this. So like it's kind of bad. As in like if you wrote everything in one language, but individual layers would be individual libraries, this would still be massively better because you could exchange code and you could refactor code more easily and stuff like this. So Mojo is trying to solve this problem by building what they claim will be a Python compatible language that will have the performance essentially world class out of any languages, because they're gonna have CMD support in an ISPC style, sort of, not quite. I don't think it's super fair, uh, but I don't think it's just intrinsics either. I hope it's not auto-vectorized. Maybe I'm overselling Mojo. I shouldn't do this because Mojo feels super oversold right now. Anyway, so like super fast implementation of everything, and then threading, GPU compute, CPU CMD compute, everything in one language, and then you write all of the code in it, and you can take a Python program and then bring it in, a Python package, and the thing has a Python interpreter running inside of it, so everything is compatible with everything. So on the surface, it seems kind of nice. There's two things I don't like about this. Neither I think are negotiable from the language perspective. I'm not disagreeing with the fact with how they're running the project. Well, there's three things they haven't. It's not like open source. It used to be they didn't have a binary. I think they have a binary now. I should double check. They just released the binary, I think, very recently, so I haven't played with this yet. The first thing I don't like about this is that by nature of defining your problem like this, you have this very difficult trade-off between how much of Python do you support and how slow, like how they have to run the Python interpreter alongside like the module code, because they have to fall back to the Python interpreter, as far as I understand, for any Python code. And then the hope is that a lot of Python code works as is in Mojo, I think. But the issue there is you still have sort of two systems that are built on very, very different kind of ideas and ideals that they have to communicate. And I'm worried that this is a problem that they claim goes away completely like it does in C++. So C++ is a C successor, and it's a language that's a superset of C. And any code that's written in C, modulo some caveats, is C++ as well. And you can mix and match, and it's zero cost. I think this is what they're going for. I'm worried that what they're going to end up with is something much more, with much more friction and performance overhead and stuff on this boundary, and that the boundary will be more like in your face than you think about. As in, I will take a random Python thing and I will try to run it in Mojo, and my expectation is, oh, it just runs. And the reality is, oh, it actually doesn't just run, and then I either rewrite it or I run it in the Python mode, and then the bridging between these things is slow. So this is my worry. I don't know if it's true. I think right now it's very, very early to say, because right now it feels like they have like 5 years of work to do still on the language, but I'm not sure. The second thing that I have concerns with is the extent to which they rely on the idea of just-in-time compilation. One problem that I have with PyTorch in all of this ecosystem is the extent to which it's JIT compiled. There is nice things about having to, like, being able to JIT compile everything, but there's also very unnice things about this. The one random example is this GPT Fast project I was talking about that I didn't get the chance to run. The first time you run it, it takes like a minute compiling CUDA kernels or something, and then the second time you run it, it takes like 15 seconds to like not compile CUDA kernels, because it has to do a lot of complex graph optimization stuff, and then end up with the same result that's already cached on disk, and then it's already cached on disk to skip some of the work. And then I've seen this over and over and over again, like in many other instances. So I just don't really like just-in-time compilation is good if this is your only option. Given an option, I would always want to go for ahead of time. So the extent to which Mojo pushes this even further is uncomfortable for me. They have this feature called auto-tuning, which, like, theoretically sounds nice. Practically, I'm like worried about this. Like, I think what they do is they run your code like with a bunch of different versions of the parameters, and then they automatically somehow measure the performance, and measuring the compiler running code, even just-in-time compiler running code a bunch of times, measuring the performance of the result, and then making a decision which of these versions to use in perpetuity scares me to like no end. So yeah, but I don't have. They started from the very reasonable starting point, which is Python code must work. Uh, you don't have an option of not running Python code if your goal is to like replace Python essentially for the ML ecosystem. Um, this is the C++ play, right? C++ had a goal basically of replacing C at the thing that C is best at, which is machine level computing. Um, Mojo has a goal of replacing Python in the thing Python is best at, which is ML computing, but at the same time gain all of the benefits of the native languages and further. And so it's like a grand unified programming language, right? For any compute sensitive, any compute efficient code that also happens to be the language that your ML researchers write code in. So it's like perfect marriage of both worlds. If you start from this assumption, you have to make the choices that they have made, I think, or a lot of them at least. I don't question this, but that's like unfortunate because I think some of the choices force you into these like paths that feel like the end result is going to be kind of weird in some ways. So anyway, that's my take. I deserve the right to change my take after actually using the language. I haven't really used the language. I'm also like waiting. So they have these amazing demos where they run code like matrix multiply, like I don't know, hundreds of thousands, tens of thousands of times faster in Python. This is an indication that Python is really slow. It's not an indication that Mojo is really fast. The thing that they have not shown at all is the GPU compute. I'm like not interested in Mojo if the only thing it does, if it perfectly replaces Python with much faster CPU compute, then I'm like interested. But as I said, I don't see how realistically that will happen. I'm not interested in this like weird fragmented version, honestly. If they manage to combine basically easy interop with Python, almost frictionless interop, even if it has a cost, excellent ability to write CPU compute efficient code, and excellent ability to write GPU compute efficient code, all in the same language, then I'm interested despite the concerns that I've brought up. This project that I'm writing is implemented entirely in C, plus a couple Python scripts to convert the models. If Mojo existed in the state where it could replace all of this, and I could rewrite the whole thing in Mojo, that could be fun. There's a fork of Llama C in Mojo, but I think it's CPU only because I think Mojo doesn't have GPU primitives yet. So anyway, I definitely one of the essentially, I'm not super watching out for Jai. I'm looking at Rust and Zig, and then I'm looking at Mojo, and then I'm not really looking at other languages to be honest, because because of all of the stuff that I discussed. Like it's interesting, like some other stuff is interesting maybe, but more like in theoretical sense. Mojo I could see given Chris Latner's track record and given the given the fact that the goals are very, very laudable, I could see this eventually making it into the set of languages that I use, which the same I can say about Rust and Zig. I honestly doubt I would seriously use Jai for projects. I doubt I would use Odin for projects, etc. So it's a worthy contender from this perspective. I wish the space was a little bit different so that a cleaner solution could be engineered. All right. Zig doesn't have operators overload. Oh my god. I didn't know this. This is a big problem. Seriously, Zig doesn't have. Oh my god. See, maybe I'm less interested in Zig now. Thank you. Well, thank you. Yeah, it's a problem. I also don't. It's a weird thing to admit. I always felt. Like there's all of the misuse arguments, etc. That all make sense. No, okay, so if your language doesn't do function overloading at all, and it doesn't do operator overloading, I guess I can respect it for some. I don't know. So they don't do operator overloading, but how do they overload like equality and stuff like this? Yeah, Halide was a big inspiration for Mojo, from what I can tell. Um, the the amount of like unreasonable hype around Mojo is one thing that frustrates me. It's a bias on my, like, it shouldn't matter at all to what extent people hype up the thing in theory, because I should be able to just look at the fundamentals. But like so right now fundamentals in Mojo are like not world shattering. They're like they feel good, but they're not world shattering. Like it doesn't feel like it has crazy ideas yet from what I've seen, but maybe I'm wrong. Um, that like people haven't tried before. Anyway, yeah, like I'd rather, maybe it's just too early to talk about this. I understand what the I understand why they're doing all of this. I guess it's just, yeah. I feel like right now a lot of the discourse that you see is, oh, it's gonna replace Python, or it's a superset. I like, so I'm not sure who says it's a superset of Python, but it's not a superset of Python, at least yet. Maybe it will be. Maybe it isn't some like under some definition of superset, but like if your expectations are formed by C and C++, then like it's not, or JavaScript and TypeScript, then it's not a superset. And will it be a superset? Maybe. Um, I think it's. I think I would describe the relationship between Mojo and Python as the relationship between Swift and Objective C, which happens to be also the thing that Chris Latter did. Maybe that's too harsh. The syntaxes are completely different. Maybe there's no perfect analogy for this, but I think, yeah, it's like not super, not like a superset right now. You can. I'm not saying they should do this. Like you can do this. It's just it's weird that they say that it is, because I don't think it is. But maybe I misunderstood something about Mojo. Maybe their claims are different, and maybe maybe some of my perception about Mojo is formed by other people talking about Mojo, not like Chris Latter talking about Mojo. So I don't know to what extent they are accurate. Uh, Anyway, yeah, I will go look into this operator overloading business. It feels, I'm surprised by this. Cause yeah, maybe they don't have function overloading in general. Eh, I need to think about this. I'm writing a lot of code in C right now, and like stuff like this hasn't really been a problem. But I'm not using any libraries. It's a very different style. If I were to think about how I would make a library that does like tensor algebra or something like this for Zig, then I would be like, it's kind of weird. But I'm not totally. The big thing, I think, about all of the things that I said, except for Rust. Rust, I have experience writing code in. So Rust, I think my opinions are relatively informed. One downside about Rust, my opinions about Rust, is that they were formed by writing Rust before it was 1.0. And I looked a little bit at the progress, and I compiled Rust code and edited Rust code, and I have some PR on some Rust project, I think outstanding, but I'm not like, I think the real way to learn if you're okay with the limitations or the issues with the language is to use it on a real project, or real as in write code in this language for a month and then we'll talk, right? So I haven't done this for Zig, and I'm not sure how much this would be a problem. Anyway, we are approaching like 3.5 hours or something like this. It's definitely time to end the stream. Thank you everyone. Sorry for the stream issues. I will figure out who I want to blame for this. It's probably Google because they made my Wi-Fi mesh. But thank you for stopping by. Hope it was entertaining even a little bit. And I will have to figure out what my stream schedule. I want to do more streams. I haven't been doing streams for a while. This is the first one in quite some time. I want to do some more programming streams, and I want to do more streams like this. But I need to figure out what's a reasonable schedule, what's a reasonable project. I thought about streaming this CUDA thing for a little bit. Maybe I'll do this, maybe I won't. We'll see. But whatever I decide will be as usual on like Twitter and Mastodon, which is the two networks I use right now. So catch you guys there, and thank you for coming. And Happy New Year. That is true. That is happening tomorrow. All right. Bye.